Everyone talks about going to Mars like it's inevitable, like it's the next chapter, and maybe it is. But the moment you land, the planet starts trying to kill you, not dramatically, but quietly, through the dirt, through the dust. What does Mars actually want to do to the human body? And do we have any answer for it? If this kind of deep look at the universe is what you come here for, make sure to give this video a like. Now let's get started. The first thing you need to understand about the Martian surface is that it is ancient and it is broken. Mars has a diameter of about 6,779 kilometers, roughly half the size of Earth. Its gravity is only 38% of what you feel standing here right now. That means if you weigh 70 kilograms on Earth, you would weigh about 26.5 kilograms on Mars. And that sounds almost appealing, maybe even freeing. But low gravity is not a gift. It is a slow catastrophe for the human body. Here is what happens. Your bones and muscles evolved over millions of years to function against Earth's gravitational pull. Every step you take, every time you stand up, every time you lift something, you are constantly reinforcing your skeletal structure. Take that away, even partially, and your body begins to let go. Bone density drops, muscles atrophy. The cardiovascular system, which is conditioned to pump blood against a particular gravitational force, starts to adapt in ways we still do not fully understand. We have seen the early signs of this in astronauts aboard the International Space Station, which orbits in microgravity. After just 6 months up there, many of them return with significant bone loss and spend months in rehabilitation. Mars' gravity is not zero, but it is far from enough to prevent these effects across the duration of a long mission. And any crewed mission to Mars would not be a 6-month surface stay. Given the orbital mechanics of getting there and returning, you would be looking at somewhere between 1.5 and 3 years away from Earth. Your body would come home different, possibly in ways that couldn't be fully reversed. But let's pull back even further, because before we talk about what Mars does to the human body over time, we need to talk about the atmosphere, or rather, the near-complete absence of one. Earth's atmosphere is a remarkable and fragile thing. It is a thin shell of gas that shields us from the vacuum of space, keeps our surface temperatures within a range that permits liquid water, and gives us oxygen to breathe. We take it entirely for granted. The atmospheric pressure at sea level on Earth is about 101,325 pascals. On the Martian surface, that pressure drops to roughly 600 pascals, less than 1% of what surrounds you right now. For context, that is comparable to being at an altitude of about 35 kilometers above the Earth's surface. No human has ever breathed unassisted air at that altitude. No human could survive it. At that pressure, the only thing keeping you alive would be whatever pressurized suit or habitat engineers manage to build and maintain without a single critical failure. But it gets worse. The Martian atmosphere is not just impossibly thin. Its composition would kill you in seconds. Roughly 95% of it is carbon dioxide. Less than 3% is nitrogen. Oxygen makes up less than 0.5%, so even if the pressure were somehow manageable, which it is not, the gas itself would still be lethal the moment you inhaled it. Your cells require oxygen to function, and Mars offers almost none of it freely. Scientists have proposed methods for extracting oxygen directly from the Martian atmosphere, a process known as in situ resource utilization. NASA's Perseverance rover actually carried a small experimental device called MOXIE, the Mars Oxygen in Situ Resource Utilization Experiment, which successfully converted carbon dioxide into breathable oxygen in a series of test runs. In its best performance, MOXIE produced about 10 grams of oxygen per hour. That is roughly enough to sustain a small plant. A resting human adult needs about 30 grams per hour to survive. Scaling that technology to support a crew of even 4 or 5 people running continuously, without failure, across years of operation, in the most resource-constrained environment humanity has ever attempted to work in. That is not a solved problem. It is one of the most complex engineering challenges our species has ever faced. And then there is the cold. Mars is cold in a way that is difficult to genuinely absorb. The average surface temperature is approximately negative 60 degrees Celsius. On a warm summer afternoon near the equator, temperatures might briefly climb to around 20 degrees Celsius, not unlike a cool autumn morning in northern Europe. But on that same equatorial ground, when the sun goes down, temperatures can plummet to negative 70 or 80 degrees Celsius within hours. Near the poles in winter, it pushes toward negative 125 degrees Celsius. For reference, the coldest temperature ever recorded on Earth was negative 89.2 degrees Celsius, measured at the Soviet Vostok station in Antarctica in 1983. Mars eclipses that regularly, just not in the places you might want to live. Those temperature swings from something approaching livable to something that freezes carbon dioxide itself out of the air as dry ice represent an extraordinary engineering challenge. Any habitat, any spacesuit, any piece of mechanical equipment you brought would have to endure that full range day after day, not for a week or a month, but for years. Materials expand and contract with thermal cycling, seals crack, electronics fail. Every cycle your gear goes through is one more opportunity for something critical to give way, far from any supply chain, any technician, any replacement part, and any meaningful help. Which brings us to the question of help, and just how alone you would truly be. The distance between Earth and Mars is not a fixed number. Both worlds orbit the Sun along different paths at different speeds, so the gap between them is always changing. At their closest approach, what astronomers call opposition, Mars can come within about 54.6 million kilometers of Earth. At their farthest, they are separated by more than 400 million kilometers. A communications signal traveling between the two planets at their nearest point takes about 3 minutes one way. At their most distant, that same signal takes more than 22 minutes. A complete round-trip exchange, sending a message and receiving a reply, can take over 44 minutes. Now imagine a medical emergency, a punctured suit, a habitat depressurization, a fire in the oxygen-rich environment of a pressurized module. In any of those moments, the people on Mars are entirely on their own. There is no real-time guidance from mission control. No emergency medical consultation happening in seconds, no rescue team gearing up. The crew must diagnose the problem, locate the solution, and execute the fix by themselves with whatever they have available, under conditions of extreme stress, in an environment that offers no margin for error. And the psychological dimension of that isolation is something researchers take very seriously. Studies of confined, isolated groups, crews in Antarctic stations, participants in simulated Mars habitat experiments, submarine crews, consistently reveal that extreme isolation under high stakes generates interpersonal conflict, decision-making errors, depression, anxiety, and in some documented cases, complete psychological breakdown. And none of those environments come close to replicating the stakes of being stranded on another planet, with no way home until the orbital windows align. There is one more thing we need to sit with before we move forward, and it may be the single most consequential hazard of all. Mars has no global magnetic field. Earth's magnetic field, generated by the churning movement of molten iron deep within our planet's core, extends far out into space around us, deflecting the solar wind, a constant, invisible torrent of charged particles streaming outward from the Sun at hundreds of kilometers per second. Without that protection, those particles would slowly strip away our atmosphere and bombard every living thing on the surface with damaging radiation. We can see the consequences of losing that shield by looking at Mars right now. Scientists believe Mars lost its global magnetic field approximately 4 billion years ago, almost certainly because its smaller core cooled and solidified more quickly than Earth's. Since then, the solar wind has been relentlessly, patiently eroding the Martian atmosphere, and it is at least partly responsible for the thin, desiccated, radiation-soaked world we see today. For any human being standing on that surface, the numbers are sobering. Data from NASA's Curiosity rover shows that the radiation dose on the Martian surface averages about 0.67 millisieverts per day. That is roughly 230 times the average daily radiation exposure a person experiences on Earth. Over a 500-day surface mission, which is a conservative estimate for a crewed stay, an astronaut would accumulate a radiation dose that substantially exceeds the career limits currently set for astronauts working aboard the space station. And that is during a relatively quiet period of solar activity. During a solar particle event, a sudden burst of high-energy radiation from the sun, the dose can spike dramatically within hours. On Earth, our magnetic field and thick atmosphere absorb the worst of it. On Mars, with almost no atmosphere and no magnetic shield, there is nowhere to run and nowhere to hide, at least not without purpose-built underground shelters or thick regolith shielding, neither of which exists yet. And here is where the story begins to shift, because humans, being the extraordinary and perhaps slightly reckless creatures that we are already imagining solutions. Underground habitats carved from the Martian rock, pharmaceutical countermeasures to slow radiation damage, selective cultivation of microorganisms that could begin, over geological timescales, to thicken and transform the atmosphere. These ideas are not science fiction. They are active areas of research. They reflect something genuinely remarkable about our species. This refusal to look at a problem and simply accept it. But imagination and engineering are not interchangeable. And the distance between what we can conceive and what we can actually construct and sustain, in a place where every kilogram of material costs an astonishing amount to transport, where a single failure can cascade into catastrophe, and where the nearest help is nearly an hour away by radio, that distance is vast. We have covered the poisoned ground, the vanishing atmosphere, the bone-deep cold, the isolation, and the invisible radiation raining down from a sky with no shield. But there is something we haven't talked about yet, something that has shut down entire missions and could define the ultimate limit of human presence on that world: the dust, not ordinary dust. Martian dust and the storms it builds are something that have to be seen to be believed. In the next part of this journey, we are going to look at what happens when the entire planet disappears beneath a cloud that lasts for months. We are going to examine what that means for power, for survival, for the psychological state of anyone trapped inside a habitat, watching the sky turn the color of a dying ember. Stay with me, because what comes next is unlike anything you have imagined about Mars. We have been talking about looking up at that faint rust-colored point of light in the night sky and understanding what it actually is. And there is something that has stayed with me ever since I first pointed a telescope at it myself. No photograph fully prepares you for the moment you see a planet with your own eyes, when it shifts from being a concept, a data point, a name you know, into a real physical glowing object hanging in actual space above your head. That moment changes something in you permanently. If you have ever wanted that experience, and I think if you are here you have, I genuinely recommend looking into the Celestron StarSense Explorer. It is a telescope that uses your smartphone to navigate the sky for you, which means you do not need any prior experience. You point it up, and it tells you exactly what you are looking at and guides you to what you want to find. Planets, nebulae, star clusters, things we talk about on this channel, now visible to you directly. It is the kind of tool that turns a curious person into someone who actually goes outside and looks. The link is in the description and pinned on the comments. And the storm in 2018, something remarkable and deeply unsettling happened on the Martian surface. A storm began, not an unusual event in itself. Mars experiences dust storms regularly, driven by the sun heating the thin atmosphere unevenly, creating pressure differences that lift fine particles off the ground. But this particular storm did not stop growing. It expanded, and then kept expanding until it had wrapped itself around the entire planet, a global dust storm, one that reduced sunlight, reaching the surface to a fraction of normal levels for weeks. NASA's Opportunity rover, a machine that had been operating on Mars for 14 years, far beyond its original 90-day mission design, a genuine triumph of engineering and perseverance, fell silent. Its solar panels, starved of sunlight by the thickening dust overhead, could no longer generate enough power to keep it running. Engineers sent signal after signal. The rover did not respond. After waiting 8 months, NASA officially declared the mission over in February 2019. Opportunity's final transmission, as reconstructed by the team, amounted to something like, "My battery is low and it's getting dark." That line broke hearts across the scientific community. And it should also tell you something profound about what a global dust storm means for any mission, crewed or robotic, that depends on solar power. Let's understand what these storms actually are, because the scale of them defies easy comprehension. Martian dust particles are extraordinarily fine, on average around 1 to 3 micrometers in diameter. For comparison, a human hair is roughly 70 micrometers wide. These particles are so small and so light that once they are lofted into the thin Martian atmosphere, they can remain suspended for months. And the mechanism that drives them into the air in the first place is a feedback loop that, once triggered, can be nearly impossible to stop. Here is how it works. As the Martian southern hemisphere moves into summer, it receives intense solar radiation because Mars has a significantly elliptical orbit, more elongated than Earth's, meaning it swings closer to the sun during southern summer than at any other point in its year. That extra heat warms the surface unevenly. Warmer regions create rising air currents. Rising air drags dust upward. Dust suspended in the atmosphere absorbs more solar radiation, warming the air further, driving stronger winds, lifting more dust. The storm feeds itself, it grows. Within weeks, it can cover millions of square kilometers. Within months, it can encircle the entire planet. During the 2018 event, optical depth, a measure of how much light the dust blocks, reached levels of over 8 in some regions. Under normal clear Martian conditions, optical depth sits around 1. The difference is staggering. Imagine going from a clear afternoon to something resembling a thick, dim, reddish twilight that lasts for months, and you begin to approach what it would feel like inside one of those storms. The sky doesn't go dark in the way you might picture. It goes a suffocating, uniform, burnt orange-brown, and it stays that way. For a crude habitat depending on solar panels, this is catastrophic. Current models for early Mars missions heavily favor solar power. It is lighter to transport than nuclear alternatives, and the technology is mature and well understood. But during a global storm, solar irradiance on the Martian surface can drop by over 99% in the worst affected areas. That is not a power reduction, that is near total loss. A crew inside a habitat watching their power reserves drain, knowing the storm might last another 3 months, would face decisions of genuine life and death severity. What systems do you shut down first? What is the minimum power threshold to keep life support running? How long do your reserves last? And, perhaps most chillingly, what happens if the storm doesn't end before those reserves run out? Nuclear power is the answer most engineers gravitate toward when this problem is raised. NASA has been developing the Killer Power project, a small fission reactor designed specifically for surface power on Mars, and it has shown real promise in ground testing. A killer power unit could potentially provide between 1 and 10 kilowatts of continuous power regardless of dust conditions. But transporting nuclear reactors across interplanetary space introduces a whole separate layer of regulatory, safety, and logistical complexity that has not yet been resolved for a crewed mission. The dust itself, independent of the storms, presents another category of problem that is easy to underestimate. Remember the perchlorates we discussed in Part 1, those toxic compounds saturating the Martian soil. Martian dust carries them. Every particle that gets lifted into the air carries traces of those chemicals, and on Mars, dust gets into everything. It coats solar panels, reducing efficiency gradually over time. It works its way into mechanical joints, causing abrasion and wear. During the Apollo missions, lunar dust, which is sharp and clingy due to its exposure to the solar wind, was one of the most frustrating and persistent practical problems the astronauts faced. Martian dust is finer, lighter, and chemically reactive in ways lunar dust is not. It would coat visors, it would find its way into airlocks. Managing contamination between the outside environment and the pressurized interior of a habitat would require engineering solutions of extraordinary precision maintained continuously for years. And here is a detail that doesn't get nearly enough attention. The perchlorates in that dust, when exposed to ultraviolet radiation, which, with no ozone layer and no magnetic field on Mars, arrives at the surface essentially unfiltered, become even more reactive and toxic. A 2017 study published in the journal Scientific Reports found that simulated Martian soil containing perchlorates, when exposed to ultraviolet light, killed bacteria within minutes. The researchers described the surface of Mars under those conditions as bactericidal, capable of destroying living cells. That is the material that would be coating your habitat, your equipment, your spacesuit every single day. Now let's talk about what all of this does to the mind. It is one thing to know intellectually that you are on another planet, 225 million kilometers from home on average, inside a pressurized shell surrounded by a poisoned, irradiated, storm-prone landscape. It is another thing entirely to live that reality across months and years. Researchers studying what they call isolated and confined environments, a field that draws on data from Antarctic research stations, submarine deployments, and long-duration spaceflight, have consistently identified a cluster of psychological effects that emerge under those conditions: increased tension and irritability, impaired decision-making, disrupted sleep, a blunting of emotional responsiveness, sometimes called the third quarter phenomenon, because it tends to peak around 3/4 of the way through a mission when the end is not quite in sight and the beginning is too far behind to draw comfort from. In 2010 to 2011, an international team of 6 volunteers participated in Mars 500, a simulated 520-day Mars mission conducted entirely inside a series of interconnected modules in Moscow, never leaving, never truly going anywhere. The psychological data gathered from that experiment was sobering. Participants experienced significant sleep disruption, reduced activity levels, and in some cases symptoms consistent with mild depression. And that simulation had one crucial advantage over the real thing. The participants knew, at some level, that the door was not actually locked, that rescue was not actually impossible, that Earth was not actually hundreds of millions of kilometers away. Real Mars astronauts would not have that comfort. There is a concept in psychology called overview effect, the profound shift in perspective reported by astronauts who have seen Earth from orbit. The fragility of it, the loneliness of it against the black, the way borders disappear, and the planet looks like one single precious living thing. It is consistently described as one of the most transformative experiences a human being can have. But here is a question researchers are beginning to ask seriously. What is the psychological effect of looking at Earth from Mars, not as a blue sphere filling your view, but as a bright star, barely distinguishable from the others, just another point of light in a dark sky, no larger than Venus appears from our surface. You could cover it with your thumb, every person you have ever known, every relationship, every place that holds meaning for you, compressed to a pinprick of light 170 million to 400 million kilometers away. Depending on the orbital geometry at that particular moment, that is not a philosophical abstraction. That is the actual lived visual reality of being on Mars. We are made, as the late Carl Sagan beautifully put it, of star stuff. The calcium in your bones, the iron in your blood, the oxygen in your lungs. Every atom of it was forged in the heart of a dying star billions of years ago and scattered across space before being gathered by gravity into a solar system, a planet, an ocean, and eventually a body capable of wondering where it came from. That is not poetry, that is nuclear astrophysics. And understanding that, really holding it, makes the question of Mars not just a logistical problem but a deeply human one. Why do we want to go? What are we reaching for? Is it survival, curiosity, the ancient biological pull toward the horizon that has driven every migration our species has ever undertaken? These are questions worth sitting with, and the honest scientific answer right now, in the year 2026, is that we do not yet have the tools, the medicine, the materials, or the psychological frameworks to send people to Mars and be confident they will come home whole. But here is the thing nobody tells you about that answer. It is not a closed door, it is an open one. In 2018, the European Space Agency's MARSIS radar instrument, aboard the Mars Express orbiter, which had been circling the planet since 2003, sent pulses of radio waves down through the Martian south polar ice cap and listened carefully to what came back. What the data revealed stopped the research team cold. Buried roughly 1.5 kilometers beneath the surface, beneath layers of ice and frozen carbon dioxide, the radar returns were consistent with something liquid, something that reflected radio waves the way a body of water would. A subglacial lake, approximately 20 kilometers across, sitting in the dark and the cold beneath one of the most inhospitable surfaces in the solar system. The team spent 3 years checking their data before they published. 3 years of verification, recalculation, and quiet, careful doubt. Because the implications were significant enough that they did not want to be wrong. When the paper finally appeared in the journal Science in July 2018, it sent a current through the planetary science community, not just because liquid water on Mars is extraordinary, but because of what liquid water, in the right conditions, can contain: life, or at least the conditions that have historically on Earth preceded it. Now, before this becomes something it is not, let us be precise. No one has found life on Mars. No organism, no fossil, no unambiguous biosignature. What has been found is suggestive geology, chemistry that doesn't immediately rule life out. And that distinction matters enormously, both scientifically and for our purposes tonight. Because the possibility that Mars might harbor microbial life, even extinct microbial life, transforms the entire question of human presence there in ways that are rarely discussed honestly. Let's start with the subsurface water question, because the 2018 discovery was not the end of the story. It was the beginning of a much more complicated one. Follow-up analysis using additional MARSIS data, published in 2020, identified not one but multiple radar-reflective zones beneath the South Polar region, a central lake surrounded by what appeared to be smaller, disconnected patches of liquid. This was exciting. It was also immediately controversial. Several research groups pointed out that the radar reflectivity observed could, under some models, be explained by other materials, certain types of volcanic rock, for example, or clays with particular mineral compositions, without requiring liquid water at all. The debate has not been resolved. It is ongoing, active, and genuinely unresolved as of the time this video was made. But here is what makes it particularly interesting from an engineering standpoint. If there is liquid water beneath the South Polar ice cap, it almost certainly cannot exist as pure water at those temperatures. The pressure from the overlying ice is significant, but probably not sufficient on its own to keep water liquid at the temperatures measured in that region, which approach -68 degrees Celsius. For water to remain liquid at those temperatures, it would need to be heavily saturated with salts, particularly perchlorates, which, as we established in Part 1, are abundant across the Martian surface and almost certainly present in the subsurface as well. Perchlorate brines can remain liquid at temperatures far below the normal freezing point of water. They are, in a sense, natural antifreeze, so what you potentially have, sitting beneath 1.5 kilometers of ice, is a dark, pressurized, hypersaline, perchlorate-rich lake in which the temperature hovers well below 0 Celsius, light has never penetrated, and the chemical environment is, by most Earth standards, deeply hostile to biology. And yet, on Earth, we have found microbial life in environments almost exactly this harsh. Lake Vostok, buried beneath nearly 4 kilometers of Antarctic ice, contains living organisms. Deep-sea hydrothermal vents host entire ecosystems in total darkness under crushing pressure. The lesson that life on Earth keeps teaching us over and over is that wherever there is liquid water and a chemical energy gradient, wherever the basic thermodynamic requirements for metabolism can be met, life has found a way to be there. That doesn't mean life is on Mars, but it means the question is not absurd. And that changes everything about the ethics of sending humans there. Here is the problem that astrobiologists and planetary protection specialists lose sleep over. If Mars has, or ever had, microbial life in its subsurface, then every crewed mission to the Martian surface carries a catastrophic risk in both directions. We could contaminate Mars with Earth organisms, potentially destroying or obscuring any native biology that exists there, making it forever impossible to know whether Martian life arose independently or was introduced by us. And going the other direction, the direction that gets discussed far less in popular coverage, we could bring something back now. The scientific consensus is that the probability of any Martian microorganism being able to infect a human being is extremely low. Life on Mars, if it exists, would have evolved in complete isolation for billions of years, under entirely different chemical and physical conditions. Its biochemistry, if it has biochemistry in any sense we would recognize, might be so alien to ours that our immune systems would have no reaction whatsoever, not because the organism is harmless, but because our biology simply wouldn't register it as a threat. That particular scenario, the silent biological incompatibility, is actually considered less dangerous than a scenario involving a Martian organism capable of exploiting Earth biochemistry. But here is what keeps planetary protection scientists focused. We don't know. We genuinely, scientifically, empirically do not know what is down there. And the consequences of being wrong, in either direction, are not reversible. You cannot uncontaminate a planet. You cannot unrelease a foreign organism into Earth's biosphere. The history of invasive species on our own world, rabbits in Australia, cane toads, zebra mussels, offers a sobering preview of what biological contamination can do to an ecosystem unprepared for a new organism, even one from the same planet. Whatever protocols and containment measures were designed for a Mars sample return mission or a crewed mission returning from the surface would need to be essentially perfect. And in engineering, there is no such thing as essentially perfect. There is only the acceptable management of risk. Now let us go deeper. Literally, in 2018, NASA landed the InSight mission on the Martian plains of Elysium Planitia. InSight, interior exploration using seismic investigations, geodesy and heat transport, was not a rover. It didn't move. It sat in one place and listened. Its primary instrument was an extraordinarily sensitive seismometer designed to detect vibrations moving through the Martian interior the way geologists use seismographs on Earth to map what lies beneath our own surface. The scientific objective was to understand whether Mars is geologically active, whether the interior of the planet is still warm, still moving, still alive in the tectonic and volcanic sense. What InSight detected, beginning in April 2019, were Marsquakes, hundreds of them. They ranged from barely perceptible tremors to events reaching magnitude 5, significant enough to be clearly detectable and informative. The data revealed that Mars has a layered interior structure, a relatively thin crust, a mantle, and a liquid outer core composed largely of iron, sulfur, and possibly hydrogen. The core radius was measured at approximately 1,830 kilometers, larger than scientists had expected, which suggests it contains more light elements than previously modeled. These findings, published across multiple papers in the journal Science in 2022, fundamentally revised our picture of Martian interior structure. But the seismic data also revealed something more immediately relevant to any future human presence. Mars is not geologically dead. There are regions of the planet, particularly around the volcanic province of Cerberus Fossae, where Marsquakes cluster, suggesting ongoing tectonic activity. Some of the most recent Marsquakes detected by InSight originated in that region, and Cerberus Fossae is not just seismically active. Geological mapping suggests that volcanic eruptions may have occurred there within the last 50,000 years, essentially yesterday in geological terms. Volcanic activity on Mars matters for human habitation in ways that cut in two very different directions. On one hand, active volcanism could be a source of geothermal heat, energy that could, in principle, be harvested without depending on solar panels or nuclear reactors. Geothermal energy might allow underground habitats to maintain temperature, power life support, and even drive chemical processes for producing water or oxygen. Iceland on Earth is powered almost entirely by geothermal sources, and it represents a compelling proof of concept for what a thermally active environment can offer. On the other hand, volcanic outgassing, the release of gases from the interior, could mean sudden local spikes in carbon dioxide, sulfur dioxide, or other compounds in an environment where the atmosphere is already at the edge of breathable. And volcanic unrest means ground instability, potential lava tube collapse, and unpredictable seismic events in precisely the kind of underground shelter where humans might be trying to hide from radiation. Lava tubes are worth pausing on because they represent one of the most frequently cited potential solutions to the radiation problem on Mars. When lava flows across a surface and the outer layer solidifies while the interior keeps moving, it can leave behind long, hollow tunnels, sometimes kilometers in length and tens of meters in diameter. On Earth, these are interesting geological formations. On Mars, where the lower gravity allowed ancient lava to flow with less resistance, these tubes could be enormous. Some estimates suggest Martian lava tubes could be hundreds of meters in diameter, far larger than anything on Earth. Their ceilings of solid rock could provide significant radiation shielding. Their stable thermal environment, insulated from the extreme surface temperature swings, might hover around -50 degrees Celsius. Still deeply cold, but dramatically more manageable than the surface extremes we discussed earlier. The idea of building a human settlement inside a Martian lava tube is not science fiction. It is an active area of architectural and engineering research. The European Space Agency has funded studies on it. NASA has considered it. There are concepts, serious ones, not just artistic renders, for inflatable habitat modules deployed inside these natural tunnels, sealed at the entrance, pressurized, and equipped to support human life indefinitely. In theory, such a structure could solve radiation, temperature extremes, and provide a degree of protection against dust storms simultaneously. In theory, the practical challenges are again extraordinary. We do not have confirmed, mapped, structurally assessed lava tubes on Mars. We have surface features that strongly suggest their presence, long, sinuous collapse chains called pit chains visible in orbital imagery, but we have never entered one. We do not know their precise dimensions, their structural integrity, whether they are fully sealed or riddled with fractures, or whether they are near any of the other resources, water ice, geothermal heat, relatively flat terrain, that would be required to make them viable settlement sites. Selecting a lava tube for a crude habitat based on orbital imagery alone would be like choosing a building site on Earth based solely on a satellite photo, without ever visiting the location or testing the ground. And beneath all of this, beneath the toxic soil and the storms and the radiation and the uncertain geology, there is a deeper question that the data keeps pushing us toward. Mars was not always like this. Roughly 3 to 4 billion years ago, Mars had a thicker atmosphere, it had a magnetic field, it had liquid water on its surface, rivers, lakes, and possibly even a shallow ocean covering much of the northern lowlands, which some planetary scientists call the Vastitas Borealis Ocean. Evidence of ancient river valleys, delta formations, and lake beds is scattered across the Martian surface and has been studied in extraordinary detail by missions including Curiosity and Perseverance. The Jezero crater, where Perseverance is currently operating, was once a lake, a real standing body of liquid water fed by an inflow river with a delta where sediment accumulated over millions of years. Perseverance has been drilling into those ancient lake sediments, collecting cores and storing them in sealed tubes to be retrieved by a future sample return mission. What happened to that Mars? Where did the water go? Where did the atmosphere go? The leading answer is the one we touched on in Part 1, the loss of the magnetic field, followed by the slow erosion of the atmosphere by the solar wind over billions of years. As the atmosphere thinned, surface pressure dropped below the threshold at which liquid water can exist, below the so-called triple point of water, where the liquid phase becomes thermodynamically unstable. Water ice sublimated directly into vapor and was gradually lost to space. What remained either froze into the polar caps and the subsurface permafrost, or was chemically bound into the minerals of the soil. Mars is, in a very real sense, a cautionary tale, a world that once had all the ingredients we associate with habitability and lost them, not through any dramatic catastrophe, but through the slow, patient, indifferent operation of physics and chemistry across geological time. We are made of the same elements as that lost Martian ocean, the same hydrogen and oxygen atoms that once flowed in a river through Jezero crater might have cycled through Earth's oceans, fallen as rain on some ancient forest, and eventually found their way into a living body. The universe recycles everything, nothing is wasted. And that continuity, that deep connection between all the matter in the solar system, is part of what makes Mars so haunting. It is not just a difficult destination, it is a mirror, a version of Earth that made it to the precipice of habitability and then was pulled back by forces no organism there, if there ever were organisms, could have understood or resisted. Looking at Mars through that lens changes something. It makes the question of going there less about conquest and more about comprehension, about understanding, with humility and precision, what it means for a planet to support life, and what it means when it stops. There is something else on Mars, though, something that has recently emerged from the data in a way that planetary scientists are still working to fully explain. Something that sits at the intersection of chemistry, geology, and the faint possibility of biology, and that the scientific community is actively, vigorously debating right now. We have not talked about the methane yet. Let's establish something clearly before we go any further, because this particular topic sits right at the edge of what science can currently say with confidence. And that edge is exactly where the most interesting things happen. Methane is a simple molecule. One carbon atom bonded to 4 hydrogen atoms. On Earth, it is everywhere, produced by living organisms, by geological processes, by the slow decomposition of organic material. It is the primary component of natural gas. Cows produce it, wetlands produce it, the deep ocean floor produces it. It is, in the context of Earth's chemistry, utterly unremarkable. On Mars, methane should not exist in any meaningful quantity. Here is why. The ultraviolet radiation streaming down onto the Martian surface, unfiltered by a magnetic field or a substantial atmosphere, is powerful enough to break apart methane molecules through a process called photolysis. Atmospheric chemistry models predict that any methane present in the Martian atmosphere would be destroyed within approximately 300 to 600 years by this radiation and by reactions with other atmospheric chemicals. In geological terms, 300 years is not even a rounding error, it is essentially instantaneous. So if you detect methane on Mars today, it was not left over from ancient times. Whatever produced it recently. Geologically, chemically, possibly biologically recently. NASA's Curiosity rover has been sitting in Gale Crater since 2012, and it has been sniffing the Martian atmosphere with its onboard instrument, the tunable laser spectrometer, part of the sample analysis at Mars suite, with extraordinary sensitivity. And it has detected methane repeatedly, inconsistently, in fluctuating concentrations that have puzzled and divided the scientific community ever since the first confirmed detection. Let's walk through what the data actually shows, because the story is more complicated and more interesting than most popular coverage suggests. Barodyl methane levels in the Martian atmosphere, as measured by Curiosity, have hovered around 0.4 parts per billion by volume. That is an almost vanishingly small amount. For context, Earth's atmosphere contains roughly 1,900 parts per billion of methane, roughly 5,000 times more. The Martian signal is faint, but it is above zero, and it should be zero, or as close to zero as makes no measurable difference. More intriguing than the background level are the spikes. On multiple occasions, Curiosity has detected methane concentrations rising sharply. The most notable spike, recorded in June 2019, reached approximately 21 parts per billion. That is more than 50 times the background level. It appeared suddenly, lingered briefly, and then dissipated. The timing was striking. It occurred during the Martian summer in the southern hemisphere, when the surface is at its warmest and surface-atmosphere gas exchange is most active. What makes this even stranger is what happened next. The European Space Agency's Trace Gas Orbiter, a spacecraft specifically designed to detect trace atmospheric gases including methane, launched in 2016 and operational from 2018, was orbiting Mars at the same time Curiosity was detecting those spikes. The Trace Gas Orbiter, with detection sensitivity down to 50 parts per trillion, looked for methane from above and found essentially none. Upper limit measurements suggested less than 0.05 parts per billion averaged across the atmosphere. Two instruments, both well calibrated, both reliable. measuring the same molecule on the same planet at the same time and arriving at contradictory results. This discrepancy is not a minor technical footnote. It is one of the genuinely unresolved puzzles of contemporary planetary science, and the scientific community has proposed several explanations, none of which has been definitively confirmed. The first possibility is that the methane is real, localized near the surface, and is being produced and destroyed so quickly that it never distributes evenly through the atmosphere. This would explain why Curiosity, sitting on the ground inside a crater, can detect it while the Trace Gas Orbiter, averaging measurements across a column of atmosphere from orbit, cannot. Some models of Martian atmospheric chemistry suggest that ultraviolet-driven reactions near the surface could destroy methane much faster than previously thought, on timescales of hours rather than centuries, which would keep it confined to a thin layer near the ground. If that is correct, it means the production source must be truly prodigious to maintain even the faint background signal Curiosity detects, because the methane is being destroyed almost as fast as it is being created. The second possibility is that the methane signal is a measurement artifact, contamination from within Curiosity's own chemistry lab, or some other instrumental effect that produces a false positive. This possibility has been seriously investigated, and, while it cannot be entirely ruled out, the Curiosity science team has gone to considerable lengths to distinguish between internal contamination and genuine atmospheric signal. The seasonal variation in methane levels, higher in summer, lower in winter, is difficult to explain as a purely instrumental artifact, because an internal contamination source would not be expected to vary with Martian seasons in that way. The third possibility, the one that generates the most careful and measured excitement among astrobiologists, is biological production. Methanogenic microorganisms, organisms that produce methane as a metabolic byproduct, are among the most ancient and resilient forms of life on Earth. They thrive in environments with no oxygen, under high pressure, in extreme temperatures, in conditions that would kill most familiar life forms. They are found in deep rock formations, in hydrothermal systems beneath glaciers. If any form of life were to exist in the Martian subsurface, in those hypothetical perchlorate brines beneath the South Polar ice, or in water-bearing fractures in the rock deeper down, methanogens are among the most plausible candidates. But, and this is where scientific discipline becomes essential, the biological explanation for Martian methane is not the most likely one. It is one of several possibilities, and it is not currently supported by any direct evidence beyond the methane signal itself. The far more probable explanations involve geology. One compelling geological mechanism is serpentinization, a chemical reaction that occurs when water interacts with certain iron and magnesium-rich rocks called ultramafic rocks. The reaction alters the mineral structure of the rock and, as a byproduct, produces hydrogen gas. That hydrogen can then react with carbon dioxide in the presence of certain catalysts to produce methane through a process called the Sabatier reaction. On Earth, serpentinization is responsible for producing methane in the deep ocean and in certain geological formations on land. Mars has abundant ultramafic rock composition, and if liquid water is moving through those formations in the subsurface, even in small quantities, even in brines, serpentinization could be actively producing methane right now, with no life involved whatsoever. Another geological possibility involves ancient methane trapped in clathrates, ice-like structures in which methane molecules are physically locked inside a cage of water ice. If Martian permafrost contains clathrates formed billions of years ago, seasonal warming of the surface could gradually release methane as those clathrates destabilize, producing the observed seasonal pattern in concentrations. The fact that the methane spikes curiosity has detected tend to occur in warmer periods is consistent with this mechanism. So we have biology, serpentinization, and clathrate release, all sitting as viable candidates. And here is the honest scientific position: we do not currently have the data to distinguish between them. What we would need to resolve the question is a lander or rover positioned close to a methane emission source, equipped to measure the isotopic composition of the gas. This is crucial. Carbon exists in several forms, isotopes, that have subtly different masses. Biological processes preferentially use the lighter carbon isotope, carbon-12, in predictable ways. Geological processes produce methane with different isotopic ratios. A measurement of the carbon-12 to carbon-13 ratio in Martian methane would provide a powerful diagnostic, not definitive proof of life, but a meaningful indicator of whether the gas was produced by chemistry or by biology. NASA's next major Mars science mission, Mars Sample Return, a collaborative effort with the European Space Agency, aims to bring back the core samples that Perseverance has been collecting. Those samples, drilled from the ancient lake sediments of Jezero crater, will be analyzed in laboratories on Earth, with instruments far more sensitive than anything that can currently be sent to Mars. If ancient organic chemistry, or something more remarkable, is preserved in those rocks, Earth-based analysis should be able to find it. But Mars Sample Return has faced significant budget pressure and schedule delays, and as of early 2026, its timeline remains uncertain. In the meantime, the methane sits there, fluctuating, appearing and disappearing, detected by one instrument and missed by another, refusing to be easily explained. Now here is why all of this matters for the question of human presence on Mars, and why it introduces a layer of complexity that most discussions of Mars colonization simply do not address. If Mars has active subsurface geology producing methane, then the planet's interior is more dynamic than many earlier models suggested. Dynamic geology means potential geological hazards, ground instability, gas emissions, unexpected subsurface voids that would need to be mapped and understood before permanent habitats could be safely established. It also means potentially accessible chemical energy sources that could be exploited for in-situ resource production. Methane is rocket propellant. If it can be captured from Martian geological sources, even in small quantities, it changes the economics of getting back off the surface. But if Mars has biology, even microbial biology buried kilometers underground, the ethical and scientific stakes become almost incomprehensibly large. The discovery of a second, independent origin of life in our own solar system would be the most profound scientific finding in human history. It would mean that life is not a miraculous accident confined to Earth. It would mean that the chemistry of life is something the universe does routinely, given appropriate conditions. It would mean that the cosmos is, in some sense, we do not yet fully understand, inclined toward life. And it would mean that every planet in every solar system, around every star in every galaxy, becomes a candidate, not a speculation, but a statistically grounded candidate for harboring living things. Contaminating Mars with Earth organisms before we have definitively answered that question would be an act of irreversible scientific vandalism, not because human exploration is wrong, but because we would be overwriting the answer before we had finished reading the question. The Office of Planetary Protection at NASA exists specifically to manage this risk. Current Mars missions are built under strict cleanliness standards designed to minimize the number of Earth organisms that hitchhike to Mars aboard spacecraft. But those standards, while rigorous for robotic missions, become almost impossible to maintain for crewed missions. Human beings are ecosystems. A single person carries trillions of microorganisms on their skin, in their gut, in every exhaled breath. No spacesuit, no airlock protocol, no decontamination procedure currently conceived could prevent some of that biological material from eventually reaching the Martian environment during a long crewed mission. The question of planetary protection in the context of human exploration is one that the scientific and policy communities are actively, sometimes heatedly, wrestling with. And there is no clean answer. Some scientists argue that if Mars has extant life, it is almost certainly confined to deep subsurface environments far from the surface, and the contamination risk from a surface mission is negligible. Others argue that we cannot know the distribution of Martian life without far more investigation than we have yet conducted, and that the precautionary principle demands we resolve the biology question robotically before sending humans. And some argue that the practical reality of human exploration makes some level of contamination inevitable, and that we should accept that and move forward while being as careful as possible. These are not comfortable conversations. They do not have comfortable answers, but they are the conversations that honest engagement with Mars demands we have. There is one more thread in this part of the story that we need to pull because it connects everything: the methane, the subsurface water, the ancient geology, the question of life, into a single, coherent picture of what Mars actually is. Mars is not a dead world. It is a diminished one. There is a profound difference between those two things, and understanding that difference is essential to understanding what going there would actually mean. A dead world is inert, static, a rock in space with a surface and nothing more. Mars is not that. Mars has weather, Mars has seasons, driven by the same axial tilt mechanism that gives Earth its seasons, though more extreme because of its more elliptical orbit. Mars has active chemistry happening on and beneath its surface. Mars has a geological interior that is still warm enough to produce seismic activity. Mars has, in its atmosphere, a molecule that should not be there. Mars has, in its ancient rock record, compelling evidence of a past warm and wet enough to have been biologically interesting. Mars is a world in a particular phase of its existence, a phase of slow decline from a more dynamic, more hospitable past, and we are arriving at what might be a critically important moment, early enough that the biological question is still open, late enough that the evidence of Mars's more habitable past is still preserved in the rock. The window for answering the most important questions about Mars is not infinite, and the way we choose to explore it, carefully or carelessly, with patience or with urgency, will determine whether we get to answer those questions at all. We began this journey on the surface, standing on poisoned ground beneath a sky that offers no protection. We went underground into uncertain geology and the possibility of ancient or even living biology. We followed a signal in the atmosphere that shouldn't exist and found that it leads not to a simple answer, but to a deeper, richer, more genuinely mysterious set of questions. And we still haven't talked about the journey itself. The months of travel through deep interplanetary space, exposed to radiation with no planet's magnetic field to shield you, no easy abort option, no way to shorten the trip if something goes wrong aboard the spacecraft. We haven't talked about what that does to the human body over 7 months of transit. We haven't talked about the bone-crushing deceleration of entry into the Martian atmosphere, a process so technically demanding that landing a vehicle the size of a crewed spacecraft on Mars remains one of the hardest unsolved problems in aerospace engineering. We haven't talked about what it takes to get off the ground on Mars once you are there, and why the rocket equation in the Martian context becomes a problem of almost terrifying proportions. There is a formula that aerospace engineers both revere and dread. It was derived in 1897 by a Russian schoolteacher named Konstantin Tsiolkovsky, working in a small wooden house in the town of Kaluga, about 190 kilometers southwest of Moscow. He had no laboratory, no funding, no institutional support. He was, by most measures of his era, an eccentric, partially deaf since childhood, largely self-educated, deeply convinced that humanity's destiny lay beyond the atmosphere, and sitting alone with mathematics he had taught himself, he derived what is now called the Tsiolkovsky rocket equation, a deceptively simple expression that describes, with absolute and unforgiving precision, the relationship between a rocket's mass, its fuel, and the velocity it can achieve. The equation looks innocent enough, but what it describes is a tyranny, a hard physical constraint from which there is no appeal, no workaround, no clever engineering trick that escapes its fundamental logic. And when you apply that tyranny to the problem of leaving Mars, not arriving, leaving, the numbers that come out are some of the most sobering in all of space exploration. Let us walk through it together, because understanding this changes how you think about everything that follows. To reach orbit from a planetary surface, a spacecraft must accelerate to what is called orbital velocity, the speed at which it is moving fast enough that the curve of its trajectory matches the curve of the planet's surface, essentially falling around the planet rather than into it. From Earth's surface, reaching low orbit requires achieving a velocity of approximately 7.9 kilometers per second. That is an enormous amount of kinetic energy, which is why rockets are mostly fuel. The Saturn V, the vehicle that carried Apollo astronauts to the moon, stood about 111 meters tall and weighed approximately 2,900,000 kilograms fully fueled. Of that total mass, roughly 85% was propellant. The actual payload delivered to the lunar surface was a tiny fraction of the total system. Now, Mars. The good news, and there is some, is that Mars is smaller than Earth, with lower gravity, so the velocity required to reach Martian orbit is lower. You need approximately 3.5 to 4 kilometers per second of delta V, which is the technical term for the change in velocity your rocket needs to produce to lift off from the Martian surface and reach orbit. That is meaningfully less than the roughly 9 to 10 kilometers per second of delta V needed to reach Earth orbit from the ground. But here is where the tyranny of the rocket equation begins to assert itself. Every kilogram of propellant you burn to reach that velocity had to be carried to Mars in the first place. And carrying propellant to Mars requires burning more propellant to get it there, which itself had to be carried, requiring more propellant, requiring more carrying, a recursive, exponentially multiplying problem that engineers call the tyranny of the rocket equation. Every unit of mass you want to move at the end of the chain requires a disproportionately larger amount of mass at the beginning to put real numbers around this. A crude Mars ascent vehicle, the rocket that would lift astronauts from the Martian surface to orbit, where they would rendezvous with a waiting Earth return ship, would need to be a substantial piece of hardware. Current NASA and SpaceX architectural concepts estimate that a Mars ascent vehicle would need somewhere between 15 and 30 tons of propellant to perform the ascent, depending on the vehicle design and the specific trajectory used. 30 tons, that is 30,000 kilograms of fuel that somehow has to be on the Martian surface, loaded and ready before the crew even lands. Transporting 30,000 kilograms of propellant from Earth to Mars is not a realistic proposition for an early mission. The cost and logistical complexity would be staggering, which is why the baseline architecture for almost every serious crewed Mars mission concept, including NASA's design reference architecture and SpaceX's Starship-based plans, relies on in-situ propellant production, making the fuel on Mars from Martian resources before the crew arrives. The chemistry for this is well understood. Mars's atmosphere is 95% carbon dioxide. If you bring hydrogen from Earth or extract it from Martian water ice, you can combine it with that carbon dioxide in a chemical reaction called the Sabatier process to produce methane and water. The methane becomes rocket propellant. The water can be electrolyzed, split by electricity into hydrogen and oxygen, with the oxygen serving as the oxidizer for the rocket engine and the hydrogen being recycled back into the Sabatier process. The whole system, in principle, is a closed loop that takes carbon dioxide and water as inputs and produces rocket propellant as output, powered by electricity from solar panels or a nuclear reactor. In principle, MOXIE, the oxygen-producing experiment aboard Perseverance that we mentioned in Part 1, was a small-scale demonstration of one piece of this technology. It worked. That is genuinely significant. But MOXIE at its best produced about 10 grams of oxygen per hour, operating intermittently. The Mars ascent vehicle we are describing would need approximately 25 tons of liquid oxygen as oxidizer alone. To produce that quantity at MOXIE's demonstrated rate would take approximately 285 years of continuous operation. Clearly, a scaled-up system, orders of magnitude larger than MOXIE, would be required. NASA's concept for a full-scale in-situ resource utilization plant envisions something the size of a small car that would need to operate continuously for approximately 26 months before a crew arrives, producing and storing propellant for the return journey. That plant would need to land safely on Mars. It would need to deploy and begin operating autonomously. It would need to run without failure, or with only minor, self-correctable failures, for over 2 years in an environment of extreme cold, dust, radiation, and perchlorate chemistry. Only once its propellant tanks were verified full would a crewed mission be launched from Earth, because if the plant fails, if the tanks are not full when the crew lands, there is no going home. This is not a theoretical edge case. It is the critical path dependency that sits at the heart of every realistic Mars mission architecture. And it is why, when engineers talk privately about the challenges of Mars, the return journey is often described as the hardest part of the whole endeavor. Let us talk about the journey to Mars itself, because the transit, the 7-month voyage through interplanetary space between Earth and the Red Planet, presents its own category of hazards that are distinct from anything we encounter on the surface. The most important of these is radiation, and the numbers, when you look at them carefully, are genuinely confronting. In the space between Earth and Mars, there is no planetary magnetic field to deflect charged particles. There is no thick blanket of atmosphere to absorb them. There is nothing but the thin protection offered by the walls of the spacecraft and whatever water, polyethylene, or purpose-built shielding material the engineers have managed to incorporate into the vehicle design. The radiation environment in interplanetary space comes from 2 primary sources: galactic cosmic rays, high-energy particles that have traveled from outside our solar system, accelerated by stellar explosions and other energetic events across the galaxy, and solar energetic particles, bursts of charged particles ejected by the Sun during solar flares and coronal mass ejections. Galactic cosmic rays are the more insidious of the two. They arrive continuously from all directions, and they are extraordinarily energetic, so much so that conventional shielding actually makes the problem worse. When a high-energy cosmic ray particle strikes a dense shielding material, it can produce a cascade of secondary particles, a shower of lighter fragments that collectively deliver more radiation dose to the people inside than the original particle would have on its own. This counterintuitive phenomenon is called secondary radiation, and it means that simply adding more metal to the walls of a Mars spacecraft does not straightforwardly reduce the crew's radiation exposure. The physics of shielding against galactic cosmic rays is an active area of research, and no fully satisfactory solution currently exists for a long-duration deep space mission. Data from the Curiosity rover's radiation assessment detector, which measured the radiation environment during its cruise from Earth to Mars aboard the Mars Science Laboratory spacecraft in 2011 to 2012, recorded a total dose of around 300 millisieverts over the approximately 253-day journey. That is equivalent to roughly 300 chest X-rays, accumulated over 8 months of travel. Round trip, accounting for both the outbound and return journeys, a Mars crew would accumulate somewhere between 600 and 1200 millisieverts from transit radiation alone before accounting for surface exposure. The career radiation limit for NASA astronauts, designed to limit excess lifetime cancer risk to no more than 3%, is 500 millisieverts. A Mars transit under current shielding technology would exceed that limit for a substantial portion of the mission, and that is during a period of average solar activity. If a major solar particle event occurs during transit, which cannot be predicted with sufficient advance warning to allow meaningful evasive action, the dose received in a matter of hours could be acutely dangerous. Solar particle events can produce doses of 1000 millisieverts or more in a short period. Acute radiation syndrome, radiation sickness, begins at doses around 1000 millisieverts. At around 4000 millisieverts without medical treatment, half of all exposed individuals die within 60 days. A spacecraft caught in a severe solar particle event with inadequate shielding could lose crew members before it ever reaches Mars. The engineering response to this threat is the storm shelter, a small, heavily shielded compartment within the spacecraft, typically located near the center of the vehicle and surrounded by water tanks, food stores, and other hydrogen-rich materials that are more effective than metal at attenuating solar particle radiation. The idea is that during a solar event, the crew retreats to this shelter and waits it out. But storm shelters add mass, and mass is the enemy of every interplanetary mission budget. And even in a storm shelter, galactic cosmic ray exposure continues unabated. Beyond radiation, the transit raises the same physiological concerns we discussed in the context of surface gravity, but intensified. For 7 months, the crew is in microgravity, true weightlessness. Bone density drops faster in microgravity than in the partial gravity of the Martian surface. Muscle mass decreases. Fluid shifts toward the head, creating elevated intracranial pressure that has been linked to vision problems in long-duration astronauts aboard the space station, a condition called spaceflight-associated neuroocular syndrome, or SANS, which in severe cases has caused lasting changes to astronauts' eyesight and optic nerve structure. The precise mechanism is still being studied, and there is currently no fully effective countermeasure. Then the crew arrives at Mars. After 7 months of microgravity, with reduced bone density, reduced muscle mass, potentially compromised vision, and accumulated radiation exposure, they now have to perform one of the most technically demanding operations in all of spaceflight, entering the Martian atmosphere and landing safely on the surface. The problem of landing large payloads on Mars has a name among aerospace engineers. They call it the 7 minutes of terror, though the more precise and comprehensive term is the entry, descent, and landing problem, or EDL, and it is a problem that, as of today, remains unsolved for the scale of vehicle needed to land humans. Here is why it is so difficult. Mars has an atmosphere, but barely one. It is thin enough that aerodynamic drag is minimal compared to what you experience entering Earth's atmosphere. But it is thick enough that you cannot simply use rockets to slow down from orbital velocity to landing speed without carrying an enormous amount of propellant, more than any realistic mission could afford. You need the atmosphere to do some of the work. But the atmosphere is so thin that traditional parachute technology, which works brilliantly on Earth and was used successfully on robotic Mars missions, cannot generate enough drag to safely slow a large vehicle at the altitudes and speeds involved. The largest object ever successfully landed on Mars using a parachute-based system was Perseverance, which weighed about 1,025 kilograms. A crewed Mars lander would weigh somewhere between 20 and 40 tons, roughly 20 to 40 times heavier. The physics of scaling parachute systems to handle that mass in the thin Martian atmosphere runs into fundamental aerodynamic limits. The parachute required would need to be so large that manufacturing, packing, deploying and reliably inflating it at supersonic speeds in a thin atmosphere becomes an extraordinary engineering challenge that has not yet been solved. NASA tested a technology called the low-density supersonic decelerator, essentially a large inflatable drag device meant to supplement parachutes for heavier payloads. Across several test flights between 2014 and 2020, results were mixed. The program was subsequently redirected. SpaceX's Starship architecture proposes to solve the EDL problem primarily with propulsive landing, using powerful engines to slow the vehicle from supersonic speeds to a gentle touchdown, but this requires carrying enormous amounts of propellant specifically for the landing burn, which feeds back into the mass problem we discussed earlier. Entry, descent, and landing for a crewed Mars mission is not a solved problem. It is not close to being a solved problem. It is one of the hardest challenges standing between current capability and actual human boots on Martian ground. And let us say, for the sake of following the full thread of this journey, that all of it works. The in-situ propellant plant arrives and functions perfectly for 2 years. The crew launches from Earth in a radiation-shielded spacecraft with a functional storm shelter. They survive the 7-month transit in reasonable health. They enter the Martian atmosphere and land precisely on target near their pre-positioned habitat and propellant facility. Spend 500 days on the surface, navigating the toxic dust, the radiation, the temperature extremes, the psychological weight of isolation. The propellant plant has filled the ascent vehicle's tanks completely. They suit up, climb aboard, and light the engine. The ascent vehicle lifts off and climbs toward orbit. In Martian orbit, they rendezvous with the Earth return vehicle that has been waiting for them. They transfer aboard and begin the 7-month journey home. More radiation, more microgravity, more physiological deterioration stacked on top of what has already accumulated. They enter Earth's atmosphere, moving at approximately 11 kilometers per second, requiring a heat shield capable of handling the most demanding re-entry in human spaceflight history. They land. They are pulled out of the capsule because after 7 months of transit each way and 500 days on a low-gravity surface, they may not be able to walk under Earth's gravity unassisted for weeks or months. They made it. The total mission duration, somewhere between 2 and 3 years. The total radiation dose accumulated by each crew member likely exceeding career limits by a significant margin. The long-term health consequences, uncertain and studied in a population of exactly 0 Mars veterans because none exist yet. The cost, estimates for a crewed Mars mission range from $100 billion to $1 trillion US, depending on the architecture, the timeline, and the assumptions baked into the model. None of this means it cannot be done. Human beings crossed oceans in wooden ships, with no GPS, no weather forecasting, no understanding of germ theory, and a navigation technology that required you to measure the angle of the sun above the horizon with a brass instrument and do trigonometry by hand. They crossed continents on foot. They flew through the sound barrier in experimental aircraft held together with rivets and faith. Every great expansion of human presence has been preceded by a period in which the obstacles seemed insurmountable, and then, slowly, through ingenuity and will, and the willingness to accept some irreducible level of risk, they were surmounted. But those expansions were built on honest assessments of what the obstacles actually were. Not optimistic projections that glossed over the hard parts, not promotional timelines designed to inspire rather than inform. Honest, rigorous, sometimes uncomfortable accounting of what it would actually take, and what it might actually cost in treasure, in time, and in human lives. That honesty is what we owe this endeavor. That honesty is what Mars demands of us. We are creatures of stardust, reaching back toward the stars. That impulse is among the most beautiful things about us. But the stars and Mars do not care about our impulses. They respond only to physics, and physics, as Tsiolkovsky understood alone in his wooden house in Kaluga more than a century ago, is not negotiable. We have covered the surface, the subsurface, the atmosphere and its impossible methane, the engineering gauntlet of landing and leaving. But there is a dimension of the Mars challenge we have not yet addressed, and it may be the one that ultimately matters most. Not the engineering, not the biology, not even the radiation, the human mind. What does isolation on that scale, true, absolute, planetary isolation, actually do to the people inside it? What do the simulations tell us? What do the psychological studies of Antarctica and submarines and sealed habitat experiments reveal about the interior landscape of a person 200 million kilometers from everyone they have ever loved? And is there a version of the Mars challenge that accounts not just for the body's survival, but for the soul's? If you are enjoying this journey, make sure to give this video a like and subscribe to the channel. You will be part of a community that explores the cosmos together. There is a moment that researchers who study isolated and confined environments have identified across dozens of studies, across multiple cultures, across wildly different mission types and durations. They call it in the clinical literature the psychological nadir, the low point, the moment or the stretch of weeks when the accumulated weight of confinement, monotony, interpersonal friction, and distance from everything familiar becomes almost physically tangible, when the walls feel closer than they did the week before, when the faces of the people you are confined with, people you like, people you respect, people you chose to be here with, begin to grate in ways that feel disproportionate and that you cannot entirely control. On a submarine, this moment is survivable because the mission ends in weeks. At an Antarctic research station, it is survivable because resupply flights eventually arrive and winter eventually ends. Aboard the International Space Station, it is survivable because the crew knows with certainty that in 6 months they will be home. On Mars, none of those lifelines exist. The mission does not end when the psychology demands it. The resupply flight cannot come early. And home, a pale blue pinprick of light in a sky that offers no comfort, is between 170 million and 400 million kilometers away, depending on where the two planets happen to be in their orbits. The crew cannot leave, they can only endure, and what endurance means, stretched across 500 days on the surface, plus 7 months of transit in each direction, is something we have never actually tested on a human being in real conditions. We have approximations, we have simulations, we have data from environments that resemble Mars in some ways, but not in the way that ultimately matters most, the actual non-negotiable impossibility of return. Let us begin with what the science actually tells us, because it is both more nuanced and more sobering than popular discussions of Mars psychology tend to acknowledge. The most comprehensive body of research on human psychology in isolated and confined environments comes from several decades of Antarctic research station studies, particularly the winter-over programs at stations like Concordia, a joint French-Italian facility located at an altitude of about 3,233 meters on the Antarctic plateau, where crews of between 13 and 16 people spend approximately 9 months in complete isolation during the polar winter, with no possibility of evacuation except in the most extreme medical emergencies. Concordia is considered the closest Earth analog to a Mars mission in terms of isolation, confinement, and the practical impossibility of escape. The European Space Agency has been conducting psychological and physiological research on Concordia crews for years, explicitly framing the data as Mars-relevant. What that data shows is a consistent pattern of psychological change across the winter-over period. In the early weeks, crews are engaged and energized. Everything is new. There is novelty in the environment, and the work, social bonds are forming. As months pass, a phase of adaptation sets in, routines establish, novelty fades. The psychological demands of constant proximity to the same small group of people become more apparent. Then comes the nadir, typically around the 2/3 mark of the mission, characterized by increased interpersonal conflict, reduced motivation, disrupted sleep, and what researchers describe as a cognitive slowing, a measurable reduction in the speed and accuracy of information processing. After the nadir, there is often a partial recovery as the end of the mission approaches and becomes psychologically real. But here is what makes the Mars scenario qualitatively different from Concordia. At Concordia, the end of the mission is fixed, known, and approaching. Crews can count down, they can mark calendars, they can see the psychological finish line, even when they cannot yet reach it. On Mars, the timeline is governed by orbital mechanics, specifically by the alignment of Earth and Mars that creates a viable return window. Those windows occur roughly every 26 months. If a crew arrived on Mars and then experienced a crisis, a medical emergency, a critical habitat failure, a psychological breakdown, the planet does not care. The window does not open early. The orbital geometry of the solar system proceeds indifferently on its own schedule, regardless of what is happening inside a pressurized shell on the Martian surface. The Mars 500 experiment, conducted between 2010 and 2011 in Moscow, remains the most ambitious attempted simulation of the psychological dimensions of a Mars mission. 6 men, a multicultural crew of Russian, European, and Chinese participants, spent 520 days inside a sealed facility, a series of interconnected modules totaling about 550 cubic meters of living space. They could not leave. They communicated with the outside world only through simulated mission control channels with an artificial time delay. They conducted simulated Mars surface excursions in spacesuits inside a separate chamber filled with sand. The physiological and psychological data collected over those 520 days revealed several consistent findings. Sleep quality deteriorated progressively across the mission. Crew members slept longer but less restoratively, experiencing shifts in their circadian rhythms likely driven by the absence of natural light cycling. Physical activity decreased substantially as the mission progressed. Crew members moved less, exercised less, and spent more time sedentary despite access to exercise equipment. 3 of the 6 participants showed signs of what researchers described as subclinical depression during the mission, not severe enough to meet full diagnostic criteria, but characterized by low mood, reduced motivation, and social withdrawal. Critically, the simulation had one factor that made it fundamentally unlike a real Mars mission. The participants knew, at some level, that if something went truly wrong, the door could be opened. The psychological contract underlying their endurance included an implicit escape clause that no real Mars crew would have. Several researchers have argued that this fundamental difference, the certainty of irreversibility, may produce psychological effects in a real mission that no Earth-based simulation can fully capture or prepare people for. There is a concept in existential psychology, sometimes called the awareness of finitude, the psychological weight of knowing at a visceral rather than merely intellectual level that a situation is bounded in ways you cannot control. Humans are extraordinarily good at suppressing this awareness in everyday life. We know we are mortal, but we do not feel our mortality every waking moment. We know our relationships will end, but we do not experience that knowledge as a constant presence. The mind has extraordinary mechanisms for managing existential awareness, distraction, routine, social connection, the simple busyness of daily life. On Mars, some of those mechanisms break down. The knowledge that you cannot come home, not because you do not want to, but because the physics of planetary orbits makes it impossible for a specific period of time, is not an abstract fact. It is the lived texture of every morning you wake up in that habitat. Every communication delay that reminds you of the distance, every time you look at that star in the Martian sky and try to identify it as home. Researchers have coined a term for a specific psychological state that may emerge in deep space explorers, Earth out of view phenomenon. It refers to the loss of the intuitive, emotionally grounding visibility of the home planet, the thing that astronauts on the space station can always access by looking out a window and seeing that luminous, familiar blue curve filling their field of view. From Mars, Earth is not a curve, it is a point, and at certain orbital positions, it is not even particularly bright. Sleep. Let us spend a moment on sleep, because it is both more important and more complicated in the Mars context than it is typically given credit for. The Martian day, called a sol, is 24 hours and 37 minutes long. That is remarkably close to the Earth day, and it is one of the genuinely fortunate coincidences of Mars exploration. Future human settlers would not have to adapt their circadian rhythms to a dramatically alien day length the way they might on a planet with a very different rotation rate. But 37 extra minutes per day accumulates. Over the course of a 500-day surface mission, the cumulative drift between Martian local time and Earth reference time adds up to roughly 13 days. Mission control at NASA operates on Earth time. Communication windows, planned activities, and logistical coordination all reference Earth-based schedules to varying degrees. The gradual, persistent misalignment between biological time, local planetary time, and mission scheduling time creates a chronic, low-level circadian disruption that is not dramatic enough to be immediately incapacitating, but is persistent enough to contribute meaningfully to the cognitive and emotional degradation that longer missions produce. NASA has studied this specific problem in the context of Mars rover operations, where science teams operating on Earth have had to adapt their schedules to Martian time. A remarkably difficult adjustment that mission teams have described as similar to the experience of permanent jet lag, requiring actual humans on the surface to navigate that same mismatch, compounded by confinement and isolation, adds another layer to the cognitive load already imposed by radiation, physical deconditioning, and the psychological weight of distance. Now, interpersonal dynamics. Because the crew is not just a collection of individuals experiencing isolation in parallel, they are a small social system, and small social systems under pressure behave in ways that are not always predictable from the individual psychology of their members. Group dynamics in confined, high-stakes environments have been studied extensively in organizational psychology, military research, and the history of exploration. The patterns that emerge consistently are striking in their regularity. Almost universally, isolated groups develop a phenomenon researchers call us versus them displacement, where interpersonal tensions within the group are managed, at least partially, by redirecting frustration outward toward mission control, toward the people who made decisions about the mission that the crew now lives with, toward the institutional structure of the space agency. In some Antarctic and spaceflight studies, this outward displacement has helped maintain within group cohesion by giving the crew a shared, external focus for their frustration. In other cases, it has produced a breakdown of communication with mission control that compromised mission safety. The crew size matters enormously. Early concepts for Mars missions proposed crews of 4 to 6 people, large enough to provide functional redundancy and some social variety, small enough to be logistically manageable, but 4 to 6 people, confined to a volume of perhaps several hundred cubic meters for 500 days, is a social environment of extraordinary intimacy and extraordinary potential for friction. You cannot choose silence without depriving the group of a contributor. You cannot choose solitude without the walls pressing in. Personal preferences, food preferences, sleep schedules, communication styles, tolerance for noise, humor that lands differently for different people, that are trivial irritants in normal life, become, under those conditions, sources of genuine interpersonal stress. Romantic relationships within the crew add another layer of complexity. No serious Mars mission architecture can guarantee that romantic or sexual relationships will not develop between crew members during a 2 to 3 year mission. The historical record of long-duration isolated groups suggests that such relationships are essentially inevitable, and when they develop within a group of 4 to 6 people in a closed system, the social dynamics that result, the realignments of loyalty, the creation of subgroups, the exclusion dynamics, can be operationally significant. There is a piece of research from Antarctic winter for over studies that has stayed with me since I first encountered it, because it captures something essential about the interior landscape of extreme isolation that clinical language tends to flatten. Researchers conducting psychological interviews with winter-over participants at multiple Antarctic stations found a recurring phenomenon they called long eye, a kind of extended, unfocused gaze that crew members would fall into during periods of inactivity, staring at a fixed point for minutes at a time, apparently without conscious direction. It was not dissociation in the clinical sense. Participants were alert and responsive when engaged. It was more like the mind finding a way to briefly step outside the walls it had been inside for months, a small, private act of interior escape that the body facilitated when the physical environment offered none. Imagine that look. Imagine what it means to arrive at the point where your mind, without being asked, simply stops engaging with the space around you and retreats inward, because inward is the only direction left that feels like movement. Now imagine it on Mars. 500 days in, the same faces, the same habitat, the same rust-colored view through a reinforced porthole, the same hum of life support systems, the same communication delay when you reach for the voices of the people you love, and the knowledge, sitting quietly behind everything, that the orbital window home does not open for another 200 days. That is not a failure of technology. It is not a failure of engineering or chemistry or medicine. It is a confrontation with something the human species has never faced before in quite this form. The test of whether a mind built for the social complexity of an African savanna, hardened across hundreds of thousands of years of evolution, to depend on community, on familiar landscape, on the cyclical rhythms of seasons and relationships, and returning home, can endure with grace and function in a place where none of those things apply, and yet people have always gone anyway. That is the other truth. Ernest Shackleton's crew spent nearly 2 years stranded on sea ice in the Antarctic after their ship was crushed in 1895, with no rescue coming and no certainty they would survive. They endured. The early polar explorers who wintered in darkness for months in wooden huts, with no communication with the outside world and no reliable hope of rescue, they endured. The astronauts of Apollo 8, the first humans to leave Earth's gravitational influence entirely, looking back at a planet reduced to the size of a marble, they endured. And what allowed them to endure across all of those cases, was something that no amount of engineering can manufacture, but that is absolutely essential to any Mars mission that hopes to succeed: purpose. A sense, not just intellectual but visceral and felt, that what they were doing mattered, that the discomfort and the danger and the distance served something larger than themselves, that their suffering, if it came to that, was not random, not wasted, but invested in something that would outlast them. The people who will go to Mars, whenever that day comes, will need that sense of purpose, not as an inspirational slogan, but as a psychological foundation that holds their identity together across years of the hardest conditions any human being has voluntarily entered. They will need it not in the first week, when everything is new and the adrenaline of arrival is still coursing through them, but in month 17, when the novelty has been completely consumed by routine and the routine has been completely consumed by fatigue. Psychologists who consult on space mission planning have proposed a range of countermeasures for the psychological challenges of long-duration space flight. Regular video communication with family and friends, though the communication delay on Mars makes real-time conversation impossible. Pre-recorded messages can be exchanged. Virtual reality environments that recreate familiar places, a walk through a forest, a visit to a childhood home, the sensory texture of rain on pavement. Carefully designed habitat interiors with variable lighting, access to plants and greenery, personalized private spaces that give each crew member a physical territory that is genuinely their own. Psychological support from Earth-based professionals who monitor crew well-being through regular assessments and maintain ongoing therapeutic relationships with crew members despite the distance. These interventions are thoughtful, they are evidence-based, and they are almost certainly insufficient on their own. The honest assessment, which the research community increasingly converges on, is that the most powerful predictor of psychological resilience in isolated and confined environments is not any particular intervention or technology. It is crew composition, choosing the right people and, critically, the right combinations of people. Individuals who are not just individually resilient, but who are specifically compatible with each other in ways that will sustain functional, respectful, mutually supportive relationships across years of pressure is the single most important variable in the psychological success or failure of a long-duration mission. And selecting for that compatibility with anything approaching confidence remains one of the most difficult unsolved problems in human factors research. We do not yet have psychological screening tools that can reliably predict how specific combinations of specific people will function together 2 years into an unprecedented mission under unprecedented conditions. We have reasonable proxies, we have assessments that identify likely problem areas, but certainty, not yet. We are creatures of astonishing resilience. The history of human exploration makes that clear beyond any reasonable doubt. We have gone into environments that should have killed us and come back changed but alive, carrying knowledge that changed everything that came after. That capacity, that willingness to go anyway, knowing what might happen, because not going feels like the greater loss, is one of the most genuinely remarkable things about our species. And we are creatures of stardust, reaching across the void toward a world that our sun once warmed enough to hold liquid water on its surface, that may once have harbored something alive in its ancient oceans or rivers, that now sits cold and scoured and silent beneath a sky that offers neither shelter nor welcome. We are reaching toward it because that is what we do, because the horizon has always called to us more loudly than the safety of the known. But the mind that will have to live on Mars, that will have to function and decide and maintain relationships and find meaning day after day in a landscape that has no precedent in human experience, That mind deserves to be understood as fully as the rocket equation, as carefully as the radiation numbers, as honestly as the perchlorate chemistry. The interior wilderness of extreme isolation is not a soft problem or a secondary concern. It may be the defining challenge of the entire endeavor. We have not yet talked about one thing that ties all of these threads together. We have talked about the surface, the subsurface, the atmosphere, the engineering, the psychology, but we have not yet talked about the timeline, about when, realistically and honestly, any of this might actually happen, about who is planning to go and what their plans actually look like when held up against the physics and the biology and the psychology we have been exploring together. In September 2016, Elon Musk stood on a stage in Guadalajara, Mexico, and presented a vision. He called it the Interplanetary Transport System. The slides showed a massive stainless steel rocket lifting off from a launch pad in a blaze of light, carrying 100 passengers toward Mars, landing propulsively on the Martian surface, refueling from locally produced methane and oxygen, and returning to Earth, ready to fly again. The architecture was audacious to the point of seeming fictional. The timeline he suggested for the first uncrewed cargo missions was 2018, for the first crewed missions somewhere around 2024. It is now 2026. No cargo mission has flown to Mars. No crewed mission is on a confirmed launch manifest with hardware that's passed human certification. The Starship vehicle, which evolved from the Interplanetary Transport System concept and is the foundational element of SpaceX's Mars architecture, has made significant progress. Its integrated flight tests have demonstrated remarkable capabilities and revealed real engineering challenges in roughly equal measure. The vehicle is extraordinary. The ambition behind it is genuine. But the gap between a Starship that can reach Earth orbit reliably and a Starship that can land humans safely on Mars and bring them home is not a gap of months. It is a gap of years, possibly decades, and it contains within it nearly every hard problem we have explored across the previous 6 parts of this journey. Let us be fair and precise here, because this is not a story of failure. It is a story of the difference between what is possible in principle and what is achievable in practice, and understanding that difference is essential to having an honest conversation about Mars. SpaceX has accomplished things that were widely considered impossible before they accomplished them. Returning orbital rocket boosters to a landing pad after flight, a technology that aerospace engineers debated for decades as either impractical or prohibitively expensive, is now routine. The Falcon 9 booster has been recovered and reflown more than 200 times. Starship, when it works as intended, will be the most capable launch vehicle in human history by a significant margin, capable of lifting over 100 tons to low Earth orbit in a fully reusable configuration. These are not incremental advances. They are genuine paradigm shifts in the economics of access to space, and they matter enormously for any serious Mars program. But the Mars mission architecture that SpaceX has publicly described requires not just a Starship that reaches orbit. It requires a fleet of Starships, multiple tanker flights to refuel the Mars-bound ship in Earth orbit before departure, a propellant production plant pre-positioned on Mars and operating successfully for approximately 2 years before any crew arrives, a crewed transit vehicle with life support systems validated for 7-month deep space exposure, surface habitats capable of supporting human life for 500 days in the Martian environment, medical facilities capable of handling surgical emergencies without resupply, radiation shielding sufficient to keep cumulative crew dose within survivable, ideally within career limit, parameters, and all of this coordinated and executed without any of the institutional redundancy and safety oversight frameworks that government space agencies have developed over decades of human spaceflight. Each of those elements is a significant engineering program in its own right. Integrating them into a functioning, safe, human-rated mission system is an undertaking of staggering complexity, and complexity in high-stakes engineering is where failures live. NASA's own timeline for crewed Mars missions has shifted repeatedly across administrations and budget cycles. The agency's current framework, the Moon-to-Mars architecture, envisions using the Artemis lunar program as a proving ground for the technologies and operational experience needed for Mars. The logic is sound. The Moon is close enough to allow real-time communication and meaningful rescue capability, far enough to test life support, surface operations, and in-situ resource utilization at genuine scale, and sufficiently demanding to surface engineering failures before they become fatal on a mission where there is no rescue. The Artemis program itself has experienced significant delays and cost overruns. The Space Launch System, NASA's heavy lift vehicle for Artemis, cost approximately $23 billion to develop and costs approximately $4.1 billion per launch. For context, SpaceX's Falcon Heavy, which can lift roughly half the payload of SLS to low Earth orbit, costs approximately $90 to $150 million per launch. The economics of NASA's current heavy lift approach are widely criticized within the aerospace community as unsustainable for the launch cadence that a Mars program would require. But economics, as important as they are not the deepest challenge. The deepest challenge is the one that money cannot simply purchase: the irreducible complexity of keeping human beings alive in deep space for years, in conditions that no amount of Earth-based testing can fully replicate, with no possibility of emergency intervention from Earth. Let us talk about what a realistic, responsible crewed Mars mission would actually require, not as a promotional exercise, but as an honest engineering and scientific assessment. Because when you lay out the requirements with precision, the scale of what remains to be done becomes apparent in a way that no amount of inspiring imagery can obscure. First, radiation. We need either a dramatically more effective passive shielding technology, something that does not suffer from the secondary radiation problem of dense materials and that does not add prohibitive mass to the spacecraft, or an active shielding system. Active shielding involves generating a magnetic or electrostatic field around the spacecraft to deflect charged particles, mimicking what Earth's magnetic field does naturally. The concept has been studied for decades. The technology exists in prototype form, but generating a magnetic field strong enough to meaningfully deflect galactic cosmic rays around a spacecraft requires enormous amounts of electrical power and produces engineering complications, structural stress, interference with onboard electronics, field geometry challenges that have not yet been solved at mission-relevant scale. This is not a problem that is close to resolution. It is an area of active research with no confirmed solution pathway. Second, closed-loop life support. The International Space Station, for all its sophistication, is not a genuinely closed system. It relies on regular resupply flights carrying food, water processing chemicals, spare parts, and other consumables. A Mars mission cannot resupply. Everything the crew needs for 2 to 3 years must either be carried from Earth or produced on Mars. The water recovery systems on the space station recover approximately 90% of water from urine, humidity, and other sources, a remarkable achievement but not sufficient for Mars. Food production in space, growing crops in a microgravity or low-gravity, high-radiation, low-light environment, has been demonstrated in small-scale experiments, but nothing approaching the caloric production needed to significantly supplement or replace carried food stores. A crew of 4 consuming roughly 2,000 calories each per day for 3 years requires something in the neighborhood of 2 million calories of food, plus packaging, plus storage, a mass budget that strains even the most optimistic Starship payload estimates. Third, medical capability. In a hospital on Earth, treating a serious medical emergency, a ruptured appendix, a stroke, a compound fracture, a cardiac event, involves teams of specialists, advanced imaging equipment, a pharmacy, an operating theatre, and the ability to escalate care rapidly if the situation deteriorates. A Mars crew has none of that. They have whatever medical training mission planners have given them, which, for non-physician crew members, amounts to advanced first aid and specific procedure training, and whatever medical equipment could be justified in the mass budget. Telemedicine consultation with Earth is possible, but the communication delay means that a physician on Earth cannot guide a procedure in real time. The crew member performing an appendectomy on a crewmate in a Martian habitat, because the alternative is death, must be competent to complete that procedure from memory without real-time guidance, under conditions of significant psychological stress, with surgical tools that have been sitting unused for potentially hundreds of days and may or may not be performing as designed. No current Mars mission architecture has fully resolved the medical capability problem. It is frequently acknowledged as a challenge and then set aside for future study. But future study is not a plan, and the consequences of inadequate medical capability on Mars are not recoverable. Now, let us turn to something that gets discussed even less than the engineering challenges: the governance problem. Who is in charge on Mars? This question sounds almost philosophical until you consider its practical implications. A crew of 5 or 6 people isolated on another planet, making decisions that affect their collective survival. How does authority work? When the mission commander makes a call that another crew member believes is wrong, potentially fatally wrong, what is the recourse? On the International Space Station, disputes can ultimately be escalated to mission control, which has final authority over mission-critical decisions. On Mars, with a communication delay of up to 22 minutes each way, mission control cannot exercise real-time authority. The crew is functionally autonomous. Historical precedent from isolated exploration is instructive but not entirely reassuring. The early Antarctic expeditions, submarine deployments, and remote research station operations all developed informal governance structures that sometimes worked and sometimes did not. The Bird expedition of 1933–34, one of the earliest and most ambitious overwintering Antarctic programs, produced documented incidents of severe psychological breakdown and near-violent interpersonal conflict within the crew that were suppressed in official accounts for years. The official narrative of exploration has always tended to emphasize triumph over difficulty rather than failure, both because the difficulties are uncomfortable to admit and because the people involved have strong institutional incentives to present their work in the best possible light. A Mars crew would need a governance framework, clear, agreed upon, and psychologically robust, for making decisions under conditions of disagreement, emergency, and incapacitation. If the commander becomes incapacitated, medically, psychologically, or otherwise, who leads? If the crew fractures into opposing factions over a critical resource decision, what mechanism resolves the dispute? These questions have legal and constitutional dimensions that humanity has never had to address in a context like this before, because no human being has ever been genuinely, physically beyond the reach of any legal or political authority on Earth. The Outer Space Treaty of 1967, the foundational document of international space law, establishes that nations retain jurisdiction over their nationals in space, and that space exploration shall be carried out for the benefit of all mankind. It says nothing meaningful about conflict resolution between crew members on a Mars surface, about property rights in Martian resources, or about the authority of a private company, as distinct from a nation-state, over a crew it has transported to another planet. These are not hypothetical edge cases. They are foreseeable scenarios that current law and policy have not addressed. Let us talk about the private versus public dimension of Mars exploration, because it sits at the intersection of all these challenges in a way that shapes everything. The dominant narrative of Mars exploration in the current era is one of a private enterprise leading where government has been too slow and too cautious to go. SpaceX's progress is real and it is remarkable. The Starship vehicle is a genuine technological achievement. The economic model that SpaceX has pioneered, reusable rockets, commercial launch services, iterative design, has transformed the cost structure of access to space in ways that benefit everyone, including NASA's Mars ambitions. But private enterprise operates under a different accountability framework than government space agencies. When a government space agency loses crew members, as NASA did in the Apollo 1 fire of 1967, in the Challenger disaster of 1986, and in the Columbia disaster of 2003, the consequences are investigated by independent government boards with full subpoena authority. The findings are made public, corrective actions are mandated, and the entire program is paused until the safety culture and the engineering have been demonstrably improved. The process is painful and slow, and sometimes politically distorted, but it exists, it has teeth, and it has, over time, produced a human spaceflight safety record that, while not perfect, reflects decades of learned lessons written in terrible cost. A private, crewed Mars mission would operate under a different framework. The regulatory oversight of commercial human spaceflight in the United States is currently governed by the FAA's Office of Commercial Space Transportation. For launches from US soil, the FAA has authority over public safety, meaning the safety of people on the ground. For the safety of the people inside the spacecraft, commercial human spaceflight currently operates under what is called a learning period, during which Congress has largely prohibited the FAA from imposing safety regulations on the interior of commercial spacecraft or the treatment of informed consent passengers, people who accept the risk voluntarily. The rationale was to allow the industry to develop without being strangled by premature regulation. Whether that rationale is still appropriate when applied to a crewed Mars mission, a mission from which there is no rescue, no abort, and no meaningful informed consent because no one can truly consent to risks they cannot fully understand, is a question that no regulatory body has yet answered. There is a broader philosophical dimension to all of this that deserves to be named directly because it runs beneath every technical and logistical question we have raised. Why are we going to Mars? Not in the abstract, inspirational sense, to ensure the survival of humanity, to become a multiplanetary species, to fulfill our destiny as explorers. Those are answers that resonate emotionally and that contain genuine truth. But in the specific operational sense, what scientific questions are so urgent, so important, and so incapable of being answered robotically that they justify risking human lives in the near term before the engineering is mature, before the medical capability is sufficient, before the psychological and governance frameworks are in place? Robotic Mars exploration has been extraordinarily productive. The Curiosity and Perseverance rovers have transformed our understanding of Martian geology and geochemistry. Ingenuity, the small helicopter that flew as a technology demonstration aboard the Perseverance mission, performed 66 flights on Mars, far exceeding its intended scope, and demonstrated powered flight in a planetary atmosphere other than Earth's for the first time in history. The Mars Reconnaissance Orbiter has produced imagery of the Martian surface, with resolution comparable to commercial satellite imagery of Earth. The InSight lander gave us our first seismic portrait of a planetary interior other than Earth's. Mars' sample return, if it proceeds, will bring back physical material from another world to be analyzed by the most sophisticated instruments humans have ever built. None of these missions required putting a human being at risk, and the scientific return from them has been profound. Human presence on Mars would accelerate exploration in ways that robots cannot match. The ability to make real-time decisions in the field, to recognize unexpected features, to collect samples from a diversity of locations across a landscape, to improvise in ways that reprogramming a rover from a distance cannot replicate. A geologist on the Martian surface would accomplish in a week what Curiosity has taken years to do. That is a real and meaningful argument for human exploration. But it is an argument about the pace and character of scientific discovery, not about its survival-level urgency. The science of Mars is proceeding without human presence, at real cost in time and scope, but without cost in human lives. The argument that compels many people most powerfully, the backup for humanity argument, the idea that establishing a self-sustaining human presence on Mars protects our species against extinction from a global catastrophe on Earth, is worth examining carefully. A self-sustaining Mars colony, genuinely self-sustaining, capable of surviving the loss of all contact and supply from Earth, would require a population of at minimum several thousand people, with the genetic diversity, the industrial capability, the agricultural production, and the institutional knowledge to maintain a technological civilization independently. That is not a near-term proposition under any realistic architecture. The early Mars settlements envisioned in current mission concepts would be fragile outposts, utterly dependent on Earth resupply, that would not survive the loss of that resupply chain for more than a few years at most. They would not constitute a meaningful backup for humanity. They would constitute an extraordinarily expensive and dangerous outpost of extraordinary scientific and symbolic value, but not an existential hedge. None of this means the dream is wrong. Let me be clear about that, because the framing of this entire journey has not been to argue against going to Mars. It has been to argue for going honestly, with clear eyes, with rigorous preparation, with the full weight of what the science tells us held clearly in mind, and translated into engineering requirements, medical capabilities, psychological frameworks, and governance structures that are genuinely adequate to the challenge. The dream of Mars is one of the most powerful and generative ideas in human culture. It has inspired generations of scientists, engineers, writers, and explorers. It has driven technological development that has produced benefits far beyond space exploration. The miniaturized electronics, the water purification technologies, the telemedicine systems, the materials science innovations, the advances in closed-loop life support, all of them have roots, at least in part, in the challenge of thinking seriously about how to keep human beings alive in extreme environments. The dream has value independent of whether it is immediately achievable. It pulls us forward. But the gap between the dream and the data, between the inspiring render and the actual physics, is not a gap of inspiration. It is a gap of solved problems. And solved problems require not enthusiasm but work, patient, rigorous, unglamorous, expensive, frequently frustrating work, the kind of work that does not generate press releases or launch live streams, but that quietly, incrementally, moves the boundary of what is achievable outward. We are moving that boundary. The InSight mission moved it, Moxie moved it, every Winter Over crew at Concordia moves it. Every robotic mission that teaches us something new about the Martian environment moves it. Every radiation biology study, every closed-loop life support experiment, every psychological resilience assessment of isolated crews moves it. The boundary is moving. It is just not moving as fast as the timelines announced on stages in Guadalajara suggested. There is something almost cosmically appropriate about the position we find ourselves in. We are a species that has been shaped across its entire evolutionary history by the tension between the safety of the familiar and the pull of the unknown. Every migration, every voyage, every summit attempt, every descent into a cave or a deep-sea trench has been an expression of that tension. Mars is simply the most extreme expression of it that our current technological moment makes conceivable. And just as our ancestors, standing on a shoreline looking at the open ocean, could not have fully imagined what lay beyond, could not have known about the scurvy that would kill their crewmates, the storms that would destroy their ships, the navigational errors that would strand them thousands of kilometers from where they intended to be, we cannot fully imagine what Mars will reveal to us, not just about the planet but about ourselves, about what the human mind and body can endure, about what we value when everything is stripped away, about what we truly are when there is no comfortable context left to define us. That is the real gift of Mars. Not the resources, not the backup planet, not even the answer to the question of whether life exists beyond Earth, though that answer, if it comes, will change everything. The real gift is the confrontation, the forced reckoning with our limits, our resilience, our ingenuity, and our humanity. We just need to go prepared for the confrontation that is actually waiting for us, not the one we imagined. We have covered 6 domains of challenge now: the surface, the subsurface, the atmosphere, the engineering of departure and return, the interior wilderness of the isolated mind, and the gap between ambition and realistic capability in the plans currently being made. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory in New Mexico. The conversation turned, as it apparently often did among that particular group of minds, to the question of extraterrestrial intelligence. Fermi listened, thought for a moment, and then asked a question so simple and so devastating that it has haunted science ever since. The question, in its most distilled form, was this: where is everybody? The universe is approximately 13.8 billion years old. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. A significant fraction of those stars, current estimates suggest more than 70%, host planetary systems. The conditions for life as we understand it, liquid water, organic chemistry, energy gradients, appear to be far more common across the cosmos than anyone imagined before the era of exoplanet astronomy. And yet, in all of that vastness, across all of that time, we have detected not a single unambiguous signal from another technological civilization. No transmission, no megastructure, no artifact, no visitor, nothing but silence, vast and deep, and, the longer you sit with it, increasingly difficult to explain. That is the Fermi paradox. Not really a paradox in the formal logical sense, more of a profound and deeply uncomfortable mismatch between what the statistics of the universe seem to predict and what our observations actually show. And Mars, cold, broken, irradiated, once warm and wet and now desiccated beyond recognition, sits right at the heart of one of the most chilling proposed resolutions to that silence. Let us build this carefully, because it deserves precision. The search for an explanation for the Fermi paradox has generated dozens of proposed solutions over the past 7 decades. Some are optimistic. Maybe intelligent life is rare, or maybe civilizations simply do not communicate in ways we have learned to detect yet. Or maybe the galaxy is so large that even a civilization broadcasting continuously for millions of years would not yet have reached us. Some are more unsettling. Maybe intelligent civilizations tend to destroy themselves before developing interstellar communication capability. maybe there is something about the development of technology that carries within it the seeds of civilizational collapse. Maybe every civilization that reaches a certain level of complexity encounters a threshold, a filter, that most do not pass through. This last class of explanation has a name, the Great Filter, a term coined by the economist Robin Hanson in 1998 to describe whatever barrier or set of barriers lies between simple chemistry and the kind of long-lived, technologically expansive civilization that would be visible across interstellar distances. The Great Filter is, by definition, something that is extraordinarily hard to pass through, something that stops almost everyone, something that converts the statistically expected abundance of advanced civilizations into the observed silence. The crucial and terrifying question is this: where is the filter? Is it behind us or is it ahead? If the filter is behind us, if the hard step was something in our past, something we have already navigated, then the silence is explained, and the future, while not guaranteed, is at least open. The hard step might have been the origin of life itself, the first self-replicating molecule emerging from chemistry, an event so statistically improbable that it has happened perhaps only once or a handful of times in the entire observable universe. It might have been the emergence of the eukaryotic cell, the complex cell with a nucleus that is the ancestor of all multicellular life on Earth, an event that took roughly 2 billion years to occur after life first appeared, and that may represent a nearly impossible leap in biological complexity. It might have been the emergence of multicellularity, or of complex nervous systems, or of language, or of the specific suite of cognitive abilities that allowed one primate species to develop cumulative technology. If any one of those steps is the filter, if the hard thing is already behind us, then we are extraordinarily lucky. We are the rare survivors. The cosmos is largely silent because life, or complex life, or intelligent life, is genuinely, almost vanishingly rare, and our path forward, however difficult, is one we have already earned the right to walk. But if the filter is ahead of us, if the hard step is something that technological civilizations encounter after reaching our current level of development, then the silence takes on a different and far darker character. It means that somewhere out ahead of us, perhaps not far, there is a wall, something that civilizations like ours run into, and almost none of them make it through. Now, Mars. Here is the connection that I want you to sit with, because it is not often framed this way, and I think it should be. Mars, 4 billion years ago, was potentially a habitable world. It had liquid water, it had a thicker atmosphere, it had a magnetic field, it had chemistry, the building blocks of life. Organic molecules, energy gradients, liquid water were present in conditions that, by Earth's standards, should have been hospitable to biology. We know this not from speculation but from the rock record that curiosity and perseverance have been reading carefully for years. Jezero Crater was a lake. The ancient river valleys of the southern highlands carried real water. The minerals preserved in the Martian crust are the minerals that form in the presence of liquid water over extended periods of time. And then Mars lost it. Not suddenly, gradually over hundreds of millions of years, as the magnetic field weakened and died, and the solar wind began its patient dismantling of the atmosphere. The water disappeared, the temperature dropped, the surface became toxic, and whatever was there, if anything was there, either retreated to the deep subsurface or was extinguished entirely. Earth, at the same epoch 4 billion years ago, was also a young, volatile, geologically hyperactive world. It had liquid water, it had chemistry, and it had, within the next few 100 million years, the first life. Microbes, simple, robust, extraordinarily tenacious microbes that altered the chemistry of the entire planet over the following billions of years, eventually producing the oxygen-rich atmosphere that made complex life possible. Two worlds, same early solar system, Similar early conditions, one kept its magnetic field, kept its atmosphere, kept its water, and produced a biosphere of extraordinary complexity that eventually generated a species capable of wandering about the universe. The other lost its field, lost its atmosphere, lost its water, and became the cold, toxic, silent world we are discussing tonight. The margin between those two outcomes, measured in the parameters of planetary science, is not enormous. Core size, cooling rate, internal heat budget, distance from the sun, differences of degree, not of kind. Small differences in initial conditions that compounded over billions of years into utterly divergent destinies. Now ask yourself this question. If we are looking for the great filter, if we are trying to understand what it is that stops civilizations from persisting and expanding across the galaxy, is it possible that we are looking at one of its mechanisms right now? Every time we send an orbiter to Mars, every time a rover drills into ancient lake sediment, every time we map the distribution of water ice beneath the Martian poles, is Mars a warning? Not in a mystical sense, in a precise planetary science sense. Is Mars showing us what happens when a world that begins with the right conditions fails to maintain them? Is the silence of Mars the silence of a world that may have had biology and lost it, or may have been on the path to biology and was redirected before it arrived, telling us something about the fragility of the conditions that allow complexity to persist? And if so, what does that mean for us, for our planet, which is also not permanent, for our atmosphere, which is also being altered by our own chemistry rather than the solar wind, but altered nonetheless? The philosopher Nick Bostrom, one of the most serious academic thinkers on the Fermi paradox, has made an argument that is deeply counterintuitive but logically compelling. He has argued that finding evidence of past or present life on Mars would be, in a specific sense, bad news for humanity. Not because Martian life would be dangerous, the planetary protection concerns we discussed earlier notwithstanding, but because of what it would imply about the great filter. If life arose independently on Mars, if the origin of life is something that happens readily, given the right conditions, as suggested by how quickly it appeared on early Earth, then the filter cannot be behind us at the origin of life step, which means it must be elsewhere, which means it is more likely to be ahead of us than we would prefer to believe. The silence of a universe that should, statistically, be full of voices becomes more ominous if we discover that the first step, life itself, is easy, because then the question becomes not why life is rare, but why complex, long-lived, technologically expansive civilizations are rare. And the candidate answers to that question are considerably less comfortable than the origin of life is just very hard. Let me be clear about something, because intellectual honesty demands it. The great filter argument is a framework for thinking, not a confirmed scientific theory. It rests on assumptions about the distribution of intelligent life that we cannot currently test directly. The Fermi paradox itself has multiple proposed solutions that do not require a filter at all. The universe is vast and old in ways that human intuition is poorly equipped to grasp. The absence of detected signals might reflect the limits of our detection methods, the physics of how civilizations actually communicate, the timescales of galactic colonization, or simply the fact that we have been listening for a cosmically trivial length of time with cosmically limited instruments. The search for extraterrestrial intelligence, SETI, has been ongoing in organized form since Project Ozma in 1960, when astronomer Frank Drake pointed a radio telescope at two nearby sun-like stars and listened for artificial signals. 66 years of listening, with increasingly sensitive instruments, across an increasingly broad range of frequencies, from an increasing number of facilities, and silence, with one famous exception, the WOW signal of 1977, a 37-second burst of narrowband radio emission detected at the Big Ear Radio Telescope at Ohio State University that bore the hallmarks of an artificial transmission and was never detected again and has never been satisfactorily explained. Nothing but 66 years is not a long time. The Milky Way is approximately 100,000 light-years across. A signal from a civilization on the far side of the galaxy, sent 66 years ago, has traveled 66 light-years. It has barely left the neighborhood, and the fraction of the electromagnetic spectrum we have systematically searched is tiny. The argument from silence is real, but it is not conclusive. The universe has not yet had the opportunity to answer at the scale of the question we are asking. What Mars gives us in this context is something irreplaceable, a nearby data point, a world where we can actually go and look, not with telescopes that can only observe indirectly, not with statistical arguments about star systems we cannot visit, but with rovers, with landers, with eventually human hands and human eyes, and ask directly, did life arise here? Did it persist? And if it arose and was extinguished, what extinguished it? The answers to those questions are among the most important data points humanity could ever gather. If Mars had life and lost it, if the planet's biology was a casualty of planetary-scale physical processes that no organism could influence or resist, that tells us something profound about the contingency of life's persistence, about how thin the margin is, about how dependent the long project of evolution and complexity is on the stability of physical conditions that are not guaranteed to last. And if Mars never had life, if, despite the liquid water and the chemistry and the energy gradients, biology never actually ignited there, that too is an extraordinary data point. It suggests that the origin of life, even given apparently favorable conditions, is rarer and harder than Earth's rapid biogenesis would suggest, which would point the filter backward toward the origin step in a way that is, paradoxically, more comforting for our long-term prospects. We do not yet know which of these is true. That is why Mars sample return matters so profoundly. That is why the question of whether Perseverance's carefully collected cores contain preserved biosignatures is not just a matter of scientific curiosity. It is one of the most important questions our species has ever been positioned to answer. And the answer, whatever it is, will reshape our understanding of our place in the universe more fundamentally than almost any other discovery in history. There is a third possibility that deserves to be named, because it is the most interesting and the most philosophically vertiginous of the three. Mars might have life right now, not fossils, not chemical traces of ancient biology, living organisms in the deep subsurface, in those hypothetical perchlorate brines we discussed, surviving in conditions so extreme that no sunlight has reached them in billions of years, drawing chemical energy from the geology around them, persisting in the dark in a kind of biological suspended animation that our instruments have not yet been designed to find. If that is true, if Mars is alive, even in that attenuated, buried, microscopic sense, then the implications are almost too large to hold. It would mean that life, once started, is extraordinarily difficult to extinguish, that even the catastrophic loss of a planetary magnetic field, the erosion of an atmosphere, the freezing of surface oceans, even all of that is not enough to end biology entirely if it has had billions of years to adapt and retreat and find refuge in the planet's interior. It would mean that the universe's inclination toward life, once expressed, persists with a tenacity that rivals any physical force. And it would mean that the two planets of our inner solar system, separated by an average of 225 million kilometers, orbiting the same star, built from the same primordial cloud of gas and dust, both harbor life. That life in our solar system is not a singularity, but a pattern. And if it is a pattern here, it is almost certainly a pattern elsewhere. Everywhere water and chemistry and energy have had time to work together. Everywhere across the 350 billion trillion stars that observational astronomy has counted in the observable universe. That thought that we might not be alone, not even within our own small solar neighborhood, is one of the most staggering things the human mind can attempt to contain. And Mars, that rust-colored dot in our night sky that human beings have been watching for thousands of years, interpreting as an omen, naming after gods of war, dreaming about going to, Mars might be the place where we finally get the answer. This is why the question of how we go to Mars matters as much as whether we go. The difference between going carefully, with the science resolved enough to know what we are dealing with the engineering mature enough to ensure a reasonable probability of return, with the planetary protection protocols robust enough to preserve the biological question's integrity, and going quickly, going before those things are true, is not just a difference in risk profile for the crew. It is a difference in what we learn, and what we learn from Mars may be the most important thing our species has ever learned about anything. We have been talking tonight about why Mars would be a terrible place to go, and it would be. The ground is toxic, the atmosphere is lethal, the radiation is relentless, the cold is bone deep, and the storms are planet-swallowing. The engineering of getting there and back is among the hardest problems our civilization has ever attempted. The psychology of surviving there, intact as a social unit and as individuals, is a frontier we have barely begun to map. The gap between current capability and what responsible human Mars exploration would actually require is real and significant. But, and this is the heart of everything, terrible and impossible are not the same thing, and the things that make Mars terrible are precisely the things that make understanding it essential. Every challenge is a question, every hazard is a data point, every piece of hostile chemistry and punishing physics is the universe telling us something about what it takes to build and maintain a world where complexity, where life, where minds like ours can arise and persist and look outward and ask, where is everybody? Mars is not just a destination, it is a mirror and it is a message, and we are only just beginning to learn how to read it. We have traveled a long way together in this journey, from the toxic soil beneath our feet to the methane signal in the atmosphere that should not exist, from the engineering gauntlet of departure and return to the interior wilderness of an isolated mind, from the gap between ambition and current capability to the deepest question in all of science, sitting quietly at the center of the Fermi paradox, waiting. There are two parts left to this journey. Now we are going to look at something that rarely gets the attention it deserves in conversations about Mars. The people who have actually dedicated their lives to solving these problems. The scientists, the engineers, the psychologists, the medical researchers, the astrobiologists, the human beings behind the missions, behind the data, behind the slowly moving boundary of what is possible. Because the story of Mars is not just the story of a planet, it is the story of a species that keeps asking questions it cannot yet answer and refuses to stop. If you are still watching, then this channel was made exactly for you. Don't forget to give this video a like and subscribe to the channel. Every video we go somewhere extraordinary together and bring back something that changes how you see everything. There is a particular kind of person who dedicates their life to a problem they know they will not personally solve, not because they lack ambition, not because they have made peace with failure, but because they understand, with a clarity that most of us never quite achieve, that the most important work is not the work that finishes in a single lifetime. It is the work that builds the foundation on which someone else, someone not yet born perhaps, will stand when the moment finally arrives. This kind of person exists in every era of exploration, In every field of science, in every engineering discipline, where the gap between current capability and the ultimate goal is measured not in years but in generations, Mars has always attracted this kind of person. And tonight, I want to introduce you to some of them, not as names attached to mission acronyms, but as human beings whose curiosity and dedication have moved the boundary of the possible in ways that rarely make headlines but that matter enormously to the story we have been telling together. Begin with Jennifer Wadsworth, a researcher at the SETI Institute whose work on Martian perchlorate, the same toxic compound we discussed in the very first part of this journey, took a turn that most people in the field did not see coming. Wadsworth and her colleague Charles Cockell demonstrated in a series of experiments published in 2017 that the interaction between Martian perchlorate and ultraviolet radiation does not merely make the surface inhospitable to life. Under UV irradiation, perchlorates react with other surface compounds to produce reactive oxygen species that are bactericidal at concentrations far lower than anyone had previously estimated. The Martian surface, their data suggested, is not just toxic. It is actively, photochemically lethal to bacteria in a way that is orders of magnitude more efficient than the perchlorate concentration alone would suggest. This was not a comfortable result. It was not a result that makes the case for finding extant surface life on Mars easier. Wadsworth knew that, and she published it anyway, because the job of science is not to produce comfortable results. It is to produce accurate ones. The willingness to follow the data somewhere difficult, to spend years developing a methodology and generating results that make your own field's hopes harder to sustain, is one of the most quietly heroic things a scientist can do. Move now to John Grunsfeld, an astrophysicist, a former NASA astronaut who flew 5 shuttle missions and performed 8 spacewalks to service the Hubble Space Telescope, and a former associate administrator for NASA's Science Mission Directorate. Grunsfeld has spoken and written extensively about the tension at the heart of NASA's Mars exploration program, the tension between the urgency of human exploration and the irreplaceable scientific value of preserving the biological question's integrity. He is someone who has floated above the Earth, who has held the Hubble telescope in gloved hands at 560 kilometers altitude, who has felt in his body what it means to be separated from the planet by the thinnest imaginable margin, and who has come back from that experience arguing, with precision and conviction, that the most important thing we can do at Mars right now is not rush. The pressure to rush is real. It comes from politics, from competition, from the natural human impatience with problems that resist rapid solution, from the genuine fear that budgets will evaporate and windows will close if momentum is not maintained. Grunsfeld's counter-argument is not that urgency is wrong, it is that the urgency needs to be calibrated against the stakes. Mars sample return, in his framing, is not a delay on the way to human exploration. It is the scientific foundation without which human exploration loses much of its deepest meaning. Now think about Fabian Knittel, not a household name, a doctoral researcher working on closed-loop bioregenerative life support systems, the technology that would allow a Mars habitat to grow its own food, recycle its own waste, and maintain its own atmospheric chemistry without continuous resupply from Earth. Knittel and researchers like him work in laboratories that are, to the casual observer, unglamorous to the point of invisibility. Tanks of nutrient solution, grow lights on timers, algae cultures and bacteria colonies, and carefully controlled atmospheric chambers. Nothing that generates the visual drama of a rocket launch or a rover descent. But the work these researchers are doing is foundational in a way that the rocket launches depend on. You can build the most capable launch vehicle in history and fill it with the most carefully selected crew ever assembled, And if the life support system fails at month 14 on the Martian surface, none of the rest of it matters. The closed-loop life support problem is not optional. It is not a detail to be worked out later. It is a prerequisite for any mission that hopes to succeed, and the people working on it, in laboratories that will never appear in a SpaceX launch livestream, deserve to be understood as central to the Mars project, not peripheral to it. Sarah Stewart Johnson is a planetary scientist at Georgetown University, whose work sits at the intersection of astrobiology and planetary protection, the discipline concerned with ensuring that our exploration of Mars does not contaminate the very environment we are trying to study. Johnson has spent years thinking carefully about what it means to look for life on another world responsibly, with the intellectual humility that the stakes of the search demand. Her book on the history of the search for life in the solar system, The Sirens of Mars, is one of the most beautiful pieces of science writing produced in the last decade. It is not a technical document. It is a meditation on the human dimensions of scientific longing, on what it means to spend a career reaching toward a question whose answer you may never personally see. Johnson's work on planetary protection is particularly relevant to the human Mars mission question. As we discussed a while ago, human beings are extraordinarily effective biological contaminants. We shed billions of microorganisms with every breath and every movement. Sending humans to Mars before we have answered the question of whether Mars harbors indigenous life is, from a scientific standpoint, a genuine risk, not to the crew but to the integrity of the question itself. Once human biology is introduced to the Martian surface, the ability to definitively determine whether any biology we subsequently detect is Martian or terrestrial in origin becomes enormously complicated. Johnson has been one of the clearest voices arguing that this trade-off deserves serious, honest attention in the mission planning process, not as a reason never to send humans to Mars, but as a reason to sequence the exploration carefully, to answer the biological question with robotic missions first, before introducing the irreversible complexity of human biological contamination. It is an argument that requires saying something that sounds, in the current cultural moment of Mars enthusiasm, almost heretical. Maybe the robots should go first, and we should listen to what they find. Before we follow, Felipe Gómez Gómez is a researcher at the Centro de Astrobiología in Madrid, Spain, part of the team that has spent years studying extremophiles, organisms that thrive in conditions considered incompatible with life by earlier generations of biologists. Gómez's work has taken him to some of the most Mars-analogous environments on Earth. The Atacama Desert in Chile, one of the driest places on the planet's surface, where certain rocks harbor microbial communities that survive by absorbing moisture directly from fog, living in conditions of ultraviolet radiation and desiccation that would destroy most organisms. The Rio Tinto River in southwestern Spain, a river so acidic and so rich in iron and sulfur compounds that it runs orange-red, a color and a chemistry eerily similar to aspects of the Martian surface, and yet teems with microbial life that has adapted over geological time to treat those conditions as home. The lesson of extremophile biology is one of the most important and most consistently surprising in all of modern science. Every time biologists have defined the outer limits of habitable conditions, the maximum temperature, the maximum acidity, the minimum water activity, the maximum radiation dose, life has subsequently been found living beyond those limits, not everywhere beyond them, and not in abundance, but present. The envelope of what biology can tolerate is larger than our models predicted, and it has been enlarged by empirical discovery every decade that we have been seriously looking. What Gómez and his colleagues are building through painstaking work in field conditions that are themselves demanding and sometimes dangerous is an increasingly detailed understanding of the actual boundaries of habitability, not the theoretical boundaries derived from laboratory conditions with pure cultures, but the empirical boundaries revealed by finding organisms alive in places they were not supposed to be. That understanding is directly relevant to the question of whether Mars, with its perchlorate, its radiation, its desiccation, its cold, is as definitively lifeless as the surface chemistry suggests, or whether life there, if it exists, has found strategies that our current models do not anticipate. Consider now the engineers, because they deserve equal billing in this story, and they do not always get it. Adam Steltzner is the chief engineer at NASA's Jet Propulsion Laboratory, who led the entry, descent, and landing team for the Curiosity rover, the team responsible for the 7 minutes of terror. Steltzner is a man who became an engineer by a route that does not fit the conventional narrative of linear achievement. He was, by his own account, a directionless young man playing bass in a rock band in the San Francisco Bay Area, when he noticed one night that the stars he was looking at after a gig had moved across the sky. He wanted to know why. The question led him eventually to community college physics courses, then to university, then to a doctorate, then to JPL, and eventually to standing in a control room at 3 in the morning, hearing the signal that confirmed Curiosity had survived its descent and was sitting intact on the floor of Gale Crater. Steltzner tells this story not as a feel-good anecdote about late bloomers, but as a specific argument about curiosity, about what happens when a genuine question, not a career aspiration, not a status goal, but a real, personal, urgent question about how something works, takes hold of a mind and refuses to let go. The entry, descent, and landing problem for Curiosity was, as we discussed, genuinely unsolved when his team began working on it. The sky crane system, the hovering descent stage that lowered the rover on cables, was not an obvious solution. It was a solution that emerged from years of working the problem honestly, following the physics wherever it led, and refusing to retreat to a familiar approach when the familiar approach could not deliver the required result. That is what the Mars problem demands of everyone working on it. Not the application of known solutions to known problems, the generation of new solutions to problems that have never been faced before. And that kind of engineering, genuinely creative, genuinely frontier-facing, requires the kind of minds that are shaped by curiosity rather than credentials. The psychologists deserve particular attention because their work is perhaps the least glamorous and most essential of all. Nick Canners is a psychiatrist at the University of California, San Francisco, who has spent 3 decades studying the psychology of spaceflight crews. His research has involved working directly with astronauts and cosmonauts on the International Space Station and with Antarctic winter-over crews on the ground. He has conducted some of the most rigorous studies of mood, interpersonal tension, and cognitive performance in isolated groups ever published, and his conclusions are both precise and sobering. Canners has consistently found that the psychological challenges of long-duration spaceflight are not primarily a function of individual psychological fragility. The people who are selected for long-duration missions are, by definition, psychologically robust. They have been through screening processes designed to identify and exclude individuals who are likely to decompensate under extreme stress. The challenges emerge not from individual weakness, but from the interaction between individuals and between the crew and the institutional structure of the mission. Use versus them dynamics between crew and mission control. Communication problems that arise from the physical distance and time delay. The specific interpersonal dynamics of small groups under sustained pressure. These are systemic phenomena, not personal failures, and they require systemic responses. Not just better individual selection, but better group dynamics training, better communication protocols, and better ongoing psychological support throughout the mission. Canners has also written extensively about something he calls the third quarter phenomenon, the tendency for psychological distress to peak at the three-quarter mark of a long-duration mission rather than at the midpoint or the end. This pattern has been observed across Antarctic winter-over studies, space station missions, and submarine deployments. The mechanism appears to be related to the shift in psychological time orientation that occurs when the crew can see the end of the mission approaching, but it is still far enough away that the approaching return offers no emotional relief, only the amplified awareness of how much time remains. On a Mars surface mission of 500 days, the three-quarter mark falls at approximately 375 days in, well past the return window calculation point, deep into the surface phase, with roughly 4 months still to go before departure preparation even begins. Understanding that the nadir of crew psychology is predictably located at that point, and building specific mission architecture, support protocols, and crew activity scheduling around that predictable low is the kind of detail that will not appear in a mission architecture PowerPoint, but that could mean the difference between a mission that holds together and one that fractures precisely when fracture is most dangerous. Turn now to someone whose work connects the biological and the geological in a way that is uniquely relevant to Mars. Bethany Ehlmann is a planetary scientist at Caltech and a co-investigator on the Perseverance rover mission. Her specialty is the mineralogy of Mars, the specific clay minerals, sulfates, carbonates, and silicates that the Martian surface and subsurface contain, and what those minerals tell us about the history of water and chemistry on the planet. Ehlmann's work has been instrumental in building the case that Mars had not just liquid water, but liquid water of varying chemistries, some environments relatively neutral, some highly acidic, some potentially alkaline, across different periods of its ancient history. This matters for astrobiology in a specific way. Life on Earth did not arise in a single chemical environment and then expand outward. It arose in conditions that we are still debating: hydrothermal vents, shallow tidal pools, ice-covered lakes, and the diversity of those candidate environments reflects the fact that chemistry has multiple pathways to the kind of self-replicating, energy-harvesting molecular complexity we call life. The diversity of ancient Martian water chemistry that Ehlmann's mineralogical work has revealed suggests that Mars, in its early history, offered not one but potentially several distinct chemical theaters in which prebiotic chemistry could have played out. If life needs a specific chemical environment to arise, Mars may have had multiple instances of that environment across its geological history. The implications are not certain, but they are significant enough that the question of Martian life deserves to be taken seriously, not as a romantic fantasy, but as a legitimate scientific hypothesis with genuine evidentiary support. And it is researchers like Ehlmann, working carefully, methodically, from the mineralogy of ancient lake beds, who are assembling the evidentiary foundation on which that hypothesis stands. There is a category of person we have not mentioned yet, and they may ultimately matter more than any scientist or engineer to the long-term story of Mars exploration: the medical doctors who are quietly working on the deep space medicine problem. Jonathan Clark is a neurologist and aerospace medicine physician who served as a crew surgeon for 6 space shuttle missions, and whose wife, Laurel Clark, was killed in the Columbia disaster of 2003. His response to that loss, to immerse himself even more deeply in the study of spaceflight safety, to devote his career to understanding and reducing the medical risks of human spaceflight, is one of the most quietly extraordinary things in the human story of space exploration. He has worked on everything from the biomechanics of parachute landing to the neurological effects of spaceflight-associated neuroocular syndrome, the condition in which the elevated intracranial pressure of microgravity causes a gradual flattening of the eyeball and structural changes to the optic nerve that can produce permanent visual impairment in astronauts after long-duration missions. Spaceflight-associated neuroocular syndrome, sometimes abbreviated as SANS, is one of the most significant unresolved medical risks of long-duration spaceflight. It was not recognized as a serious concern until relatively recently, when post-flight MRI examinations of returning long-duration station crew members revealed structural changes to the brain and optic nerve that had not been anticipated. The mechanism is not fully understood. The long-term consequences are still being studied, and the implications for a Mars mission where crew members would spend 7 months in transit microgravity each way, plus potentially months in Martian partial gravity during the surface phase, are serious enough that SANS is now listed as one of the 5 most critical human research risks that NASA's Human Research Program is working to resolve before crewed deep space missions begin. Researchers like Clark are working on countermeasures, lower body negative pressure devices that may help redistribute fluid and reduce intracranial pressure, exercise protocols, pharmacological interventions. None of them have been validated at the duration and intensity that a Mars mission would require. This is not a solved problem. It is a problem being worked on by people who understand exactly how much is at stake and who are bringing to it the same combination of scientific rigor and personal commitment that characterizes the best of human exploration. What connects all of these people? Wadsworth and Grunsfeld, and Johnson and Gomez and Stelzner and Canners and Eelman and Clark, and the hundreds of researchers and engineers and physicians whose names I have not had time to mention tonight, is not a shared certainty that Mars will be reached in their lifetimes. Very few of them believe that. And it is not a shared indifference to the challenges and the risks. They are, if anything, more aware of the challenges than anyone else, because their professional lives are organized around understanding specific challenges at the deepest possible level. What connects them is something more fundamental and more durable than certainty or optimism. It is a conviction, felt, not just thought, that the question is worth the work. That understanding the universe we inhabit, at whatever cost in time and effort and personal sacrifice that understanding demands, is among the highest things a human mind can do with its brief tenure in existence, that the problems of Mars exploration are not obstacles to something worthwhile. They are the worthwhile thing itself. The working of them is the point. The reaching is the meaning. This is the tradition of exploration at its finest, not the glamour of arrival, which belongs to a single moment and a small number of people, but the long, patient, collaborative, cumulative process of earning the right to arrive, the decades of unglamorous work that make the arrival possible. The people we have discussed tonight are not supporting characters in a story whose hero is a rocket or a billionaire or a government program. They are the story. Their curiosity is the engine. Their rigor is the fuel. Their willingness to spend careers on problems that will outlast them is the infrastructure on which whatever happens next will be built. The history of our species is, in a certain light, a history of exactly this. Of people who worked on problems they could not finish, leaving their results for people who continued the work, who left their results for people who continued it further, in an unbroken chain of human curiosity, stretching from the first stone tools to the first cave paintings, to the first writing, to the first mathematics, to the first telescope, to the first satellite, to the first footprint on the moon. Every link in that chain mattered. Every researcher who published a result that turned out to be wrong but pointed the next researcher toward the right question mattered. Every engineer who designed a system that failed and in failing revealed what needed to be done differently mattered. Every physician who identified a medical risk that no one had been looking for, and in identifying it, made it possible to address, mattered. The people working on Mars today are links in that chain, and the people who will eventually stand on the Martian surface, whenever that day comes, in whatever decade or generation it belongs to, will stand there on the accumulated weight of everything these people have done. They will breathe recycled air whose chemistry was worked out by someone whose name they will probably never know. They will be protected from radiation by shielding whose design emerged from physics experiments they were not alive to witness. They will maintain their psychological health through protocols developed by researchers whose papers they read in training, but whose faces they never saw. That is how human achievement actually works. Not in the heroic singular, but in the collaborative plural. Not in a single launch, but in 1,000 unglamorous hours of work that made the launch safe enough to attempt. We are almost at the end of this journey. One part remains, the final chapter, the synthesis, the place where all of these threads come together. We have talked about the soil and the sky and the storms, about the engineering and the biology and the psychology, about the cosmic context and the Fermi paradox and the silence that Mars sits in the middle of, about the people who are dedicating their lives to moving the boundary of the possible outward, one solved problem at a time. There is a moment in the life of every serious question when it stops being a question about the world and becomes a question about the person asking it. You begin by asking about Mars, about the soil chemistry and the atmospheric pressure and the radiation flux and the engineering margins and the psychological endurance of small groups in sealed habitats on the surface of a world that has been dead for billions of years. You follow those questions with the rigor they deserve, and the answers accumulate, and the picture becomes clearer, and also, somehow, more complex. The way that every genuine inquiry into a deep subject reveals not a simpler truth beneath the surface, but a richer and more intricate one. And then, if you have been paying close enough attention, something shifts. The questions stop pointing outward, toward the planet, and start pointing back, toward the asker, toward the species that produce the asker, toward the peculiar fact that a collection of atoms arranged in the shape of a primate on a pale blue dot orbiting an unremarkable star in the outer reaches of an average galaxy has developed the capacity to wonder about its place in a cosmos 13.8 billion years old. That shift from the question about Mars to the question about us is where this final part of our journey lives. We have established across 9 parts of careful and honest inquiry that Mars would be a terrible place to go. Not rhetorically terrible, not metaphorically terrible. Literally, physically, chemically, biologically, psychologically, and logically terrible in ways that are precise, measurable, and in several cases not yet resolved by any technology or methodology currently available to our civilization. The soil is laced with perchlorates that react with ultraviolet light to produce compounds that shred the cellular machinery of living organisms with extraordinary efficiency. The atmosphere is 95% carbon dioxide, thin enough to provide no meaningful protection against radiation, and not enough pressure to keep water liquid on the surface, which means that if you removed your helmet, your blood would not boil dramatically, as science fiction suggests, but your saliva would. The temperature swings between extremes that no unprotected human body could survive for minutes. The dust storms are planetary in scale and can persist for months, reducing sunlight to levels that would strain solar power systems beyond their operational margins. The radiation environment during the transit from Earth delivers a dose that approaches career limits for NASA astronauts before the crew has even arrived. The psychological demands of a 2 to 3 year mission in a confined habitat with a communication delay that makes real-time conversation with Earth impossible, and a return window governed by orbital mechanics rather than human need, represent a frontier in human endurance that has never been tested at real scale. All of that is true. Every word of it is supported by data from missions we have flown, experiments we have conducted, and research programs we have run. None of it is speculation dressed as science, and yet here we are, a species that knows all of this, that has the scientific and engineering capability to map these dangers with extraordinary precision, and that is, nonetheless, building the rockets, running the experiments, training the crews, studying the extremophiles and the perchlorate chemistry and the radiation biology and the closed-loop life support systems and the psychological nadir phenomena and the orbital mechanics, working patiently and expensively and with full awareness of every terrible thing that waits on the other end, toward the moment when a human being steps out of an airlock onto the Martian surface for the first time. Why? That question, not the engineering question or the biological question, but the philosophical one, the one that asks what it is about us that makes us do this, is the one I want to sit with in this final part. Because I think it is the most important question of all, and I think Mars, approached honestly, gives us an answer that is more profound and more humbling and more beautiful than any mission architecture or any inspiring speech about the destiny of our species. Let us begin with what we know about the history of our relationship with this planet. Human beings have been watching Mars for as long as human beings have been watching the sky. The ancient Egyptians called it Hadesha, the Red One. The Babylonians tracked its motion with enough precision to begin predicting its position years in advance, a mathematical achievement that required sustained, collaborative, multi-generational observation. The ancient Greeks identified it with Ares, the god of war, the reddish color suggesting blood, suggesting conflict, suggesting the dangerous and the powerful. Every major civilization in human history that developed an astronomical tradition noticed Mars, paid attention to it, tried to understand what it was and what its motions meant. For most of that history, Mars was a point of light, a reddish point that moved against the background of fixed stars in a pattern that was regular enough to be predicted, but complex enough to be fascinating. The apparent retrograde motion of Mars, where it seems to slow, stop, and briefly reverse direction in the sky before resuming its normal course, was one of the central puzzles that drove the development of mathematical astronomy in both the European and Islamic traditions. Kepler's 3 laws of planetary motion, the foundation of modern orbital mechanics, the mathematical framework that every mission to Mars depends on, were derived in large part from his years of painstaking work on the orbit of Mars, using the precise naked-eye observations of Tycho Brahe. Mars made us better at understanding motion, at understanding the geometry of the solar system, at understanding, ultimately, the force that governs all of it. Mars has been pulling human curiosity forward for thousands of years, long before we knew it had a surface we could stand on, long before we knew it had geology or a history or a complicated atmospheric chemistry, long before we knew or could have known that it was a world at all in the way we now understand the word. It pulled us because it was there, and it moved, and it was the color of something that mattered to us, and we could not look away. The first telescopic observations of Mars, Galileo's, in 1610, revealed it as a disk rather than a point. The first features resolved on that disk, the polar ice caps, the darker albedo regions that early observers named as seas and continents, were observed in the 17th century. Giovanni Schiaparelli, mapping Mars in 1877, described what he called canali, channels. On the Martian surface, a word that was mistranslated into English as canals and ignited one of the most consequential misunderstandings in the history of science. Percival Lowell, a wealthy American astronomer who built his own observatory in Flagstaff, Arizona, specifically to study Mars, spent years developing an elaborate theory of a dying Martian civilization that had constructed a planet-spanning canal system to transport water from the polar ice caps to the arid equatorial regions. He wrote 3 books about it. He gave public lectures. He generated enormous popular interest in Mars as a place where someone might live, where someone might be trying to survive, where we might not be alone. Lowell was wrong. The canals were an optical illusion, a product of the human visual system's tendency to connect disconnected features into patterns when viewing objects at the limits of resolution. There was no canal system. There was no dying civilization. There was no intelligent Martian engineer drawing water across a desiccated world. But Lowell was also, in a strange way, doing something important. He was asking the question. With all the wrong tools and all the wrong assumptions, and with a level of certainty that the data did not warrant, he was standing at his telescope on a clear Arizona night and asking, is there anyone there? Is this world inhabited? Are we alone? Those are not wrong questions. They are among the most important questions a mind can ask. And the fact that his answers were wrong does not diminish the significance of the asking. Science advances through the collision of genuine questions with rigorous methods. Lowell had the questions. He lacked the methods. The researchers who came after him, who flew spacecraft to Mars and saw not canals but craters, who landed on the surface and tested the soil and found perchlorates instead of life, who found ancient lake beds and river channels and evidence of a world that was once far more hospitable than it is today. They had better methods. Their answers are closer to the truth. But they are asking the same question, has always been the same question. Is there anyone there? The question underneath the question, the one that makes the Mars question matter so much, is of course the question about us, about what it would mean if the answer were yes, about what it would mean if the answer were no, about what our presence in this universe says, about the nature of the universe itself. We are, as Carl Sagan observed, and as the nuclear physics of stellar evolution confirms, made of star stuff. The carbon in our bodies was forged in the nuclear furnaces of stars that lived and died before our sun was born. The oxygen we breathe was scattered into the interstellar medium by supernova explosions billions of years ago. The iron in our blood was synthesized in the cores of massive stars in their final moments of existence. We are not separate from the cosmos. We are the cosmos, arranged in a particular configuration that has developed, through billions of years of biological evolution, the capacity to look back at itself and wonder. That is not a poetic gloss on a physical fact. It is the physical fact stated accurately. The universe has produced in us a means of knowing itself. Whether it has produced other such means, on Mars, around other stars, across the 350 billion trillion stars of the observable universe, is a question we do not yet know the answer to. But the fact that it has produced at least one is, when held clearly in mind, staggering, almost incomprehensibly so. We are the universe's self-awareness, or at least one instance of it, and Mars, that cold, broken, irradiated world, may be the place where we find out whether we are the only instance, whether consciousness and complexity and the capacity for wonder emerged once in a cosmic accident of almost impossible improbability, or whether they are what the universe tends toward whenever the conditions allow, whether we are alone or whether the silence, vast and deep as it is simply what it sounds like in the interval between question and answer. I want to say something now about the nature of fear, because fear has been threaded through everything we have discussed, and I think it deserves to be named directly. The data we have explored together is frightening. Not abstractly frightening, concretely, specifically, measurably frightening. Perchloric concentrations that would damage the thyroid gland with sustained exposure, radiation doses that increase cancer risk by meaningful fractions of a % per day, dust storms that could deprive a habitat of solar power for weeks, psychological nadir phenomena that occur predictably at the 3/4 mark of a mission that cannot be shortened, medical emergencies that cannot be escalated beyond the resources in the habitat, communication delays that make real-time guidance from Earth impossible, engineering challenges that remain genuinely unsolved, biological questions about Martian contamination that have no clear resolution pathway in current mission architectures. All of that is real. All of it should be taken seriously. All of it argues for caution, for rigor, for honesty about the gap between current capability and what responsible human Mars exploration requires. And none of it argues for stopping, because fear, the right kind of fear, the kind that is proportionate to actual risk and that motivates careful preparation rather than paralysis, is not the enemy of exploration. It is the precondition for doing exploration well. The explorers who went into the unknown without fear were not brave, they were careless. The ones who went knowing exactly what they were risking and prepared themselves as thoroughly as knowledge and resources allowed, they were brave. And the distinction matters enormously when the unknown you are entering is as unforgiving as Mars. The data we have explored is not an argument against going. It is an argument for going prepared, for going with the medical capability that the medical risks demand, for going with the radiation shielding that the radiation data demands, for going with the psychological frameworks that the isolation research demands, for going with the planetary protection protocols that the biological question demands, for going when the engineering is ready, not when the timeline is convenient, not when the political moment is favorable, but when the actual capability exists to give the crew a reasonable probability of coming home. There is a concept in mountaineering that most Mars-like of terrestrial pursuits, in the sense that it places small groups of human beings in environments that will kill them without hesitation if they make serious mistakes, called summit fever. The overwhelming pull toward the goal, the top of the mountain, that causes climbers to override good judgment about weather, about time, about physical condition, about the objective signs that turning back is the correct decision. Summit fever has killed more mountaineers than any other single factor, not avalanches, not equipment failure, not altitude sickness. The refusal to turn back when turning back is what the mountain is telling you to do. The history of ambitious human endeavors is full of summit fever. The space program has not been immune. The Challenger disaster, as the Rogers Commission investigation established, was in significant part a product of institutional and scheduling pressure that led decision-makers to override the technical concerns of engineers who knew, with good reason, that the O-ring performance in cold temperatures was inadequate. The mountain was telling them to turn back. The fever said go. The lesson, paid for at terrible cost, is not that ambition is wrong. It is that ambition unchecked by rigorous honesty about real conditions is not courage. It is recklessness dressed in the clothes of courage. And the difference between the two is sometimes invisible from the outside, but is always visible in the data if you are willing to look at it honestly. Mars is the highest mountain our species has ever pointed at. The summit fever around it, the enthusiasm, the urgency, the competitive pressure, the genuine excitement of a generation of engineers and scientists who have spent their careers preparing for exactly this moment is real and understandable and in many ways admirable. But the mountain is very tall and the conditions are very specific and the data is very clear about what preparing for those conditions actually requires. The most important thing we can do right now, at this particular moment in the history of our relationship with Mars, is look at the data honestly, all of it, the exciting data and the frightening data and the unresolved data and the data that tells us things we would prefer not to hear. Hold it clearly. Let it shape the timeline rather than letting the timeline shape what we choose to look at, and then go, because the alternative, not going, turning away from the question because the answer requires too much, is not actually available to us. Not really. Not to a species that has been looking at that reddish point of light for 50,000 years and asking with increasing sophistication but undiminished urgency what it is and whether it matters and whether there is anyone there. We are going to Mars. The only question is whether we go well or badly, whether we go having done the work that the work demands, or whether we go having done the work that the timeline allows, whether we go having answered as many of the hard questions as current science and engineering can answer, or whether we go having deferred those questions to the crew that will have to live with the consequences of our deferral. The choice is ours. It is being made right now in laboratories and mission planning sessions and budget hearings and engineering reviews and psychological research programs that are either well-funded or not, that are either taken seriously or not, that are either integrated into the mission architecture or left on the shelf of future study. It is being made in the culture that surrounds space exploration, in what we celebrate and what we overlook, in which achievements we treat as milestones and which risks we treat as acceptable, in whether we demand honesty from the people who are making these decisions or whether we reward the inspiring story over the accurate one. Mars has been telling us something for a long time. It told us, through the retrograde motion of its orbit, that the Earth was not the center of the solar system, a fact that rewrote our understanding of our place in the cosmos and was deeply uncomfortable and is now simply true. It told us, through Schiaparelli's Canali and Lowell's fevered imagination and the subsequent century of observation that corrected both of them, that the universe does not organize itself around our wishes. That rigorous method, not inspiring hypothesis, is how we find out what is actually there. It told us, through the data from every mission we have sent to its surface, that a world can begin with the ingredients of habitability and lose them, that planets are not permanent, that conditions are not guaranteed, that the window for complexity and biology and mind is contingent in ways that should give us pause when we look at our own world and the conditions we are introducing to it, and it is telling us something right now in the data from Perseverance's drill cores and the methane measurements from orbiting spacecraft and the seismic profiles from InSight and the mineralogical surveys from decades of orbital remote sensing. It is telling us something about the history of water and chemistry and the possibility of life that we have not yet fully decoded. That decoding, patient, rigorous, honest, is the most important scientific work our generation has been given the opportunity to do. We are, right now, at the most extraordinary moment in the 50,000-year human relationship with Mars. We are close enough to send machines that can drive across ancient lake beds and drill into ancient rock and collect samples that may contain the chemical signatures of ancient biology. We are close enough to be seriously planning the missions that will bring those samples back to Earth. We are close enough to be testing the life support technologies and the radiation countermeasures and the habitat architectures that a crewed mission will require. We are not yet ready to send people, not safely, not responsibly, not with the medical capability and the radiation solutions and the psychological frameworks that the data says we need. But we are closer than we have ever been. And in that closeness, in the gap between where we are and where we need to be, which is the gap that the people are spending their careers closing, There is something that feels less like frustration and more like momentum, like the specific sensation of a question forming that is about to be answered, like the moment before a discovery when the evidence has almost but not quite resolved into a pattern and you can feel the resolution approaching. Mars is going to teach us something. It already is, with every orbit and every landing and every carefully collected core sample. And whatever it teaches us, whether it shows us that life arose there and was extinguished, or that life arose there and persists in the deep subsurface, or that life never arose there despite conditions that seem to invite it, that lesson will be the most important thing our species has learned since we first looked up and understood that the stars were suns. It will tell us something about the probability of life in the universe, about where we sit in the distribution of possible outcomes for a rocky planet in the habitable zone of a middle-aged star, about whether the silence of the cosmos is the silence of a universe that only managed life once, or the silence of a universe so full of life that no single civilization has yet found the means to bridge the distances between its instances. And it will tell us something about ourselves, about the kind of species we are, about whether, faced with a question of this magnitude and a challenge of this difficulty, we chose to do the work honestly and patiently and well, or whether we let summit fever and competitive pressure and the human preference for inspiring stories over accurate ones lead us to cut corners that should not be cut, defer problems that should not be deferred, and arrive at the destination before we were genuinely ready for the confrontation it was always going to demand, the cosmic silence. That is the name of this channel, and it is also, tonight, the subject. The silence of the cosmos, the deep, vast, ancient quiet of a universe that has been here for nearly 14 billion years, and that, as far as our instruments can determine, has produced in all that time and all that space only one civilization capable of asking these questions, is not an emptiness. It is a pressure. It presses against the mind that contemplates it seriously, asking, what does this mean? What does it say about us that we are here, asking this? What does it say about the universe that it produced someone to ask? Mars sits in that silence, cold and broken and beautiful and haunting and full, perhaps, of answers we have not yet found the tools to read. It has been there for 4.5 billion years, accumulating the record of its own history in the rocks and minerals and potential biosignatures of its ancient surface, waiting, if that word has any meaning applied to a planet, for the moment when a curious species from the third rock out pointed its instruments at it and asked the question seriously enough to deserve the answer. We are that species. This is that moment. The answer is forming. We just have to do the work, all of it, honestly, without cutting corners, to make sure we are ready to hear it. The ground on Mars is toxic, and the sky is thin, and the storms are vast, and the cold is bone deep, and the radiation is relentless, and the distance is almost incomprehensible, and the engineering challenges are formidable, and the governance questions are unresolved, and the timeline is uncertain, and the risks are real, and the gap between ambition and current capability is significant. Mars would be a terrible place to go, and we are going anyway, because we are the species that looks at the terrible and asks what it means, because we are the cosmos contemplating itself, because the question is too important, and the moment is too extraordinary, and the silence is too full of something that might be an answer. Go carefully, go honestly, go prepared. And if Mars terrified you tonight, wait until you see what actually living there day after day would look like. That video is on your screen right now. Click it, you won't be able to look away.